All right, time is 7 o'clock, so let us start on time. Very good evening, everyone. So this is the third and the final certification program on behalf of IIIE and MTC Global joint certification program. We started with beginner certification, then we had intermediate certification, and this is the advanced level certification. Once again, I welcome all the participants on behalf of IIIE and MTC Global for this wonderful certification program. It's my great pleasure today to welcome the resource person for this workshop, and I'll just briefly introduce the resource person for the workshop. Just 1 minute. All right. We have with us Dr. Jitesh Pradhan, who is presently working as an assistant professor in Department of Computer Science and Engineering at prestigious NIT Jamshedpur. Sir has done his master's and Ph.D. from IIT-Dhanbad. He has 9+ years of research experience in the field of image processing and artificial intelligence. He has published more than 75 research articles in international journals and conferences. Sir has published 10 patents and currently part of 5 externally funded projects on application of AI in healthcare, video processing, and image processing. He is also the guest editor of a Q1 Springer journal. He is an active reviewer of 20+ renowned international journals. His research area includes image processing, DNA computing, NLP, machine learning, deep learning, feature engineering, and medical image analysis. It's a great pleasure to have Dr. Pradhan with us for this certification program, and that too in the weekend, in the evening time. All family members must be busy with their family and kids, but it's a great contribution from his side, and also all the participants for their aptitude to learn. And most of the participants, they had joined earlier 2 sessions also, and they are now at the advanced level. So I request Dr. Pradhan sir to kindly please take over. Thank you so much.
Okay, thank you, sir. Am I audible?
Yes, sir, very much.
Okay, thank you so much, sir, for such a nice introduction and for giving me this opportunity for this advanced certification program. So, shall we start, sir? Or
yes, sir, please start.
Okay, just a second, sir. I'm sharing my screen. Okay, so is my screen is visible?
Yes, sir.
Okay, sir. Just a second. Okay, so shall we start? Very good evening to all of you. Myself, Dr. Jitesh Pradhan, and today in this actually we have total 10 hours of this certification course, and we have to cover everything starting from deep learning to till that deployment of a model, we have to do a project also. Okay, so today we will be diving into the basics of deep learning, that will focus on a architecture of deep learning, how the deep learning concept come up, and it has been inspired from the actual working of our brain neurons. Then we will go to the CNN and RNN portion. Okay, so this is the outline of my today's talk. I will be covering some fundamentals of deep learning, including ANN. So in which we will see what deep learning is, what are the basic idea behind the ANN, which is artificial neural network. Then we will dive into the working of artificial neurons, perceptron model, and then we will go for a propagation of forward propagation, backward propagation. Then we will see the advantages, limitation, and applications of ANN. Then we will go to the CNN also, in which we will see the basic introduction of CNN, fundamentals related to the CNN architecture, how different layers of CNN works, that we will see the biological inspiration and visual intelligence of CNN architecture. Then we will go for a core principles of CNN, followed by evolution of deep learning architecture from its earlier version to till current version. Then we will see some real world application. Then we will go to the RNN portion. Okay, RNN stands for recurrent neural network, where we will see the need of RNN and what is the issue with the sequential data. Then we will dive into the core architecture of RNN. We will see how forward pass works. There are some problems in RNN that is called vanishing gradient problem, which is solved by another version of RNN that is called LSTM. And we will see real world application and advantages also. So these are the brief outline of today's talk. Okay, now let's start with the first, that is a fundamental of a deep learning architecture, where we will dive into the basics of deep learning architecture. Now, a basic deep learning model is basically composed of few layers. It will be having an input layer and it will be having output layer. In between, there will be some hidden layers. Okay, the hidden layers has been changed in CNN, but in deep learning is basically inspired from artificial neural network, and which basically mimics the human brain. So basically, first we need to understand the artificial neural network. Okay, then only we can understand the deep learning. So first we need to understand what is a deep learning actually. So deep learning is nothing but it's a subset of machine learning, which is a subset of AI. Okay, so basically deep learning, it's a type of a machine learning in which we feeds raw data. We already know now, I think you have already covered machine learning. So in machine learning, we give the features to a model. Okay, it should be a pattern, it should be it should be some information extracted from a raw data, then the machine learning will work. But in case of a deep learning, we will give raw information without any feature extraction, and it will work. And why we call it a deep learning actually? So the deep learning words come up from the depth of network. Okay, in most of the architecture, the number of layers are very high. Okay, where the model will try to learn from a very small features to very abstract feature. A very small features, for example, let's say if we take a picture. Okay, in picture, let's say it's a classroom picture. Then the very smallest feature will be the ages of tables. In classroom, there will be tables. Okay. In classroom, there will be tables, there will be chairs, there will be a screen. Okay, so the smallest features will be what? It will be the edges, corners, it will be the lines. Okay, and what will be the abstract feature or global features? Okay, that will be the number of faces. Okay, and number of boards, and it will try to recognize the faces in between the all the available faces. These are called, that is called abstract feature. So deep learning, what it does, it try to extract local features to global features. It means it will initially extract a very smaller features, try to learn smaller patterns, and based on that, after some layers or after some time, it will try to learn the or grasp the semantic meaning of the image. Okay, that is the major fundamental difference between machine learning and deep learning, because machine learning doesn't extract any pattern. Okay, you have to feed the pattern, it will try to learn the pattern, not it don't find the pattern. But in case of deep learning, you feed the raw data and it will try to find the pattern and learn the pattern. It will do both. Okay, that is the basic difference. Now, why deep learning? Okay, so there are major concerns. First one is the explosion of data. Okay, now nowadays, due to the digital advancements and that free internet uses, okay, internet is very easily available in all handheld devices. Okay, and people are using lots of social media, and they are uploading images, they are uploading voices, they are uploading videos. So lots of information is available in the internet. Okay, and the number of that information is growing exponentially large. Okay, so if you have to analyze something from that information, then machine learning can't do it, because machine learning needs feature. Okay, and if you have a data, let us assume that the data is containing millions of images, and try, if you want to extract a feature from millions of images, then you have to develop your own algorithm first. Then you will apply, you will try to extract features from all the images, then you will store it. So it's a very tedious process, and you don't know na, which feature will work better in which case. Okay, so here comes the deep learning, because deep learning, we don't need to extract pattern, it will automatically extract. Okay, second thing, GPU advancement. Right now we have very efficient GPU architectures. Okay, so our machine learning, so we can design very complex model and it will run efficiently, there will be no resource constraint. Okay, and day by day algorithms are getting better, we are getting better algorithms. Earlier, if you that the most we call it the most famous deep learning model was VGG. Okay, that is visual geometry group. Okay, now right now it's absolute, people are using GPT models, transformer models. So day by day people are generating better algorithms. Okay, so that's why the deep learning concept is also right now in very hype, and the real world success of deep learning is very high as compared to the machine learning models, because machine learning models completely depends on the feature extraction, and that will be done manually. You have to design some feature extraction algorithm, you don't know whether that will work in all cases or not. Okay, so that is the major problem, and that deep learning gives you the complete automation also. So these are some few reasons, that's why we are using deep learning rather than machine learning architectures. Okay, now these are some comparison between deep learning and traditional machine learning. Data requirements. Okay, so traditional machine learning, it works on a smaller data set. If a data set is small, then it will learn, because the traditional machine learning, what it does, it just try to learn the pattern. So what it will do, it will try to find the linearly separable line, or if you are using any SVM model or any other model, then it will try to find any non-linearly separable lines also. So it try to separate the data into classes only. So it will work unless the data is smaller. Okay, but in case of deep learning, you need a very high amount of data. If data is high, then there is a very high chance that the performance will also high. Now, in case of a traditional learning, you have to design the manual feature extraction process. That is called feature extraction. Okay, this feature engineering part. But in case of a deep learning, we use filters. We will see what are the filters. Okay, that will try to extract the pattern from the raw data. At the same time, it will try to learn the pattern also. That's why deep learning works better. The model complexity. Now, it's traditional machine learning are just equation based. Okay, these are simple mathematical models and very simple, and it doesn't need high GPU requirements. But in case of a deep learning, right now the models, that LLM models, GPT models, and the transformer models, these models are very complex. They need very high GPU requirements. Okay, now training time, since these traditional machine learning approaches learns on a feature now, so feature will be very less dimensional, so it will train faster. Okay, but in case of deep learning, we will try to feed the raw data. Okay, and it will take time, because it has to learn the pattern from a very local area, and it will try to mimic the overall semantic meaning also. So that's why it takes time as during training. Computational resources, it can run a CPU also, but in deep learning also, in deep learning for deep learning, we need GPU, we need TPU. TPU is specifically designed for deep learning tasks, that is called tensor processing units. So this TPU works very well, and there is a free version of TPU that you can use. Google provides TPU in its Colab. Colab is a Google Collaboratory is a platform. It's a cloud platform where you can run your codes in TPU, and it will be it works very efficiently. Okay, now interpretably, so most of this CNN deep machine learning models are equation based, and it's a pure mathematical. It just try to separate the classes, so it's a interpretable. Okay, and it's very easy to explain. But when it comes to deep learning, we often deal with a black box. It's very hard to interpret. That's why right now the people are working on a explainable AI portion, where we can explain what is happening within the black box. Okay, performance in some cases it is good if the data is linearly separable, and if the features you have extracted are efficient, then it is good. But if the problem that you are working is very complex and it is having complex pattern, then it may struggle. Okay, but in case of deep learning model, it works very efficient in a complex pattern also. Even it works on a very it works very efficiently on a image, voice, signal, as well as your video data. Example of algorithm, I think you have already seen this linear regression, logistic regression, the support vector machine, key nearest neighbor, decision tree, random forest. These are some common example of a machine learning, traditional machine learning. Whereas the initial version of deep learning was artificial neural network, ANN. Okay, then the CNN concept come up. Then there is a recurrent neural network concept come up. Then there was transformer, and currently we are doing in transformer and autoencoders. Now, it is suitable for structured tabular data, smaller data set. If the data is linearly separable, then it is very good. Okay, it works on unstructured data. Although you can pass the structured data also, but it works very efficiently on unstructured data. Unstructured data means there will be, if you have to provide the raw data. It will be image, audio, text, and video. It can be signal also. Okay, so these are just common, a very basic difference between traditional machine learning and deep learning. Here you can see that it's a traditional machine learning. If you provide raw data, then first we need to do the feature engineering. We need to try to find some type of pattern from the raw data. These are called features. So patterns are nothing but it's a low dimensional information that has been extracted from raw data and which represents it in a unique way. And what model does? Model try to fit a line. It try to find a line that perfectly fits this. Fits means it try to separate. If there is a two classes, then it will try to separate the two classes. If there is a multi classes, then there will be multiple lines, and they will try to separate the three classes from each other. So we have to just separate them. Okay, these are the traditional machine learning workflow. But in case of a deep learning, we provide raw data. Okay, the raw data will be provided into the input layer, and there will be some in between. There will be some process in the hidden layers. Okay, and at the last, it will try to predict the output. The output can be anything. It can be a classification task. It can be a regression task. It can be one generation task where we can generate image from an image. We can generate caption from an image. We can generate some type of a summary from an image. We can provide a large text data and we can summarize it. We can do translation. All the things can be done in the deep learning architectures. Okay, so now let's try to understand we have already seen that definition of a deep learning. It's basically a subset of a machine learning that uses neural networks with many layers to learn complex pattern. Now we will see what is a neural network. Okay, the inspiration, it's basically the neural network. The name neural come off from our neuron from a brain. Okay, we have a nerve system that has a neurons. So this neural network come up with that neurons because it try to mimic the working of a biological neurons. Okay, so inspiration is it's just mimicking the biological neurons in our brain. Okay, what is the major strength of it? It can handle images, speech, text, sequential data. Even it can work very efficiently on the random data also. Okay, some common examples where we can apply deep learning are image recognition, where we can use for the image recognition will be used in the self-driving cars. How? Because in self-driving car, you need to find the obstacle, you need to find the route, you need to find the path in which your car will move. So for that, you need to perform the image recognition. Okay, then we have speech assistant, we have Siri, Alexa. It's a basically voice command based searching system or voice command based. Siri can translate also, Alexa can translate also. So these are speech assistant. Okay, then we have a language translator like a Google translator. You will give input in one language and the Google translator will give you output in another language. So these are some common example where we can use deep learning. Okay, now let's start with the artificial neural network, because this neural network concept come up from the biological neuron. So what we have done, we have tried to create a artificial neural network with artificial neuron. We call it perceptron. Okay, that can mimic the biological neuron. Now let's try to see how it does. So basically, core concept is it's a computational model designed to imitate the human's brain learning process. So how it does actually. So basically, now let's take this example. There is a grandpa holding his grandson. Okay, now this child is asking, what is this? This child has seen a frog. It has seen the frog for first time. Okay, so since it has seen it first time, but it doesn't know whether it's a frog or what, it's basically a new animal to this child. So it asks to his grandparent or his grandpa, grandpa, what is this? So grandpa tells, it's a frog. Okay, now it was a green frog right now. Okay, maybe after some time he will find that there will be a brown frog. He will ask again, grandpa, what is this? Grandpa will tell, it's a frog. Okay, so every time it will see a different frog, it will try to ask his grandpa to know about the frog, whether it's a frog or anything else. Every time the grandpa will tell him that it's a frog. So during the time, okay, it's called learning. We are giving one example. At the same time, we are passing the information related to that example. The information is called as a label. Okay, and this is our raw data. So basically, it's called a supervised learning. Okay, where we have a teacher which will teach us what kind of a data we are reading. Okay, so it can be a feature also. It can be any data. Okay, so every time it will see a new data. Okay, during learning process, it will ask its teacher about the information of that data. Okay, so that teacher is nothing but it's a ground truth information. The ground truth information, in this case, it will be frog. Okay, now again, if it is saying lion, then the ground truth information will be lion. So we will pass image lion. At the same time, we will tell our model that this image is for lion. So it's how the ANN will learn. Okay, now, so basically it will be nothing but it will be learning by example in case of supervised. In case of unsupervised, the learning will be different. So most of the CNN model are supervised learning, works on a supervised learning system. Okay, most of the deep learning works on a supervised learning system. Okay, now processing data, how it will does, basically they use, in our brain there are interconnected neurons. Okay, the neurons will automatically, if the image will be, we will see an image, the neurons will be activated, and the information within the neuron will be adjusted in such a way that whenever we see this image again, our brain will tell that it's a frog. Okay, we will see how neuron works also, actually, and it's a continuous improvement process. First, you need to learn what is a frog. Then after some time, you will try to learn what is a lion. Then after some time, you will try to learn a bird. After some time, you will try to learn a cat or dog. So it's a continuous learning process, but it will be learning by example. Okay, if you are seeing a new environment or new information, then if that information is not already seen by you during your training, then you cannot predict what it is. Okay, so if you want to try to predict something, then you must have seen that information related to that information previously. Okay, that's why it's called continuous improvement. Now, shift in paradigm. Basically, unlike traditional software that relies on rigid if-else system, most of the traditional softwares, okay, they were if-else system. Whether if it is having a beak, then it's a bird. If it is having a let's say beard or something, let's say if it is jumping, then it's a frog. So it was just the if-else cases. Okay, so these type of things have been absolute. Okay, we are not using it right now. So what ANN does, ANN creates its own internal rules. It will see the image, okay, and will try to adjust its neurons, okay, in such a way that whenever we will feed this image again, then our ANN will tell that it's a frog. Okay, that is a shift in the programming. Okay, now mapping unstructured data, ANN excel in finding the hidden nonlinear relationship, especially in case of a very complex and messy data. Okay, if it's a photo, most messy data are basically images and videos. Okay, so it can map unstructured data also. Okay, so these are the basic idea of ANN. Now, the ANN has been inspired from the biology. So all of you already know now what is a neuron. Okay, now let's say it's a basic neuron in our nervous system. So in neuron, we are having a nucleus, we are having soma, that is called cell body, we are having dendrites, we are having axon. So these four things are more important. Okay, now how it does actually. So these dendrites, these are nothing but these dendrites are, let's say it's a receptors, or it can receive information. So these will be connected to other neurons. Okay, the information will pass through dendrites. Okay, the information will pass through dendrites. It will be electromagnetic. It will be electrochemical signals. Okay, in terms of electrical pulses or currents. Okay, Then nucleus, that is a soma cell body. What it will does, it will sum up all the information gathered from the dendroids. Okay, that it does. Okay, it is called processing zone also. It sum all the information gathered from the dendrites. If the sum of information passes a threshold value, then it will activate the neuron and it will pass information via axon through synapse. Okay, so that is the basic process, that it will gather information in electrochemical. These are electrochemical signals. Okay, once the soma will sum up all the signals, received signals. If the signals value is above some threshold value, let's say 5 volt, or sorry, let's say something, some 5 volt or something, then it will activate the neuron. And if the neuron will activate, what it will does, it will pass the information through synapse. Okay, synapse are nothing but these are joint points. Okay, and this axon is a output zone. It will send the output, and these joint points are where the multiple neurons will be connected. These are called synapse. Okay, this is a basic principle of a ANN. Okay, now let's see how this our artificial neural network can be inspired from the neuron. Now we have taken this, it's an artificial neuron. Okay, we call it a perceptron. Here we have a synaptic terminals. Look at synaptic terminals are these terminals. Okay, it's a terminals on the dendrites where it will connect to other neurons. Okay, here the information inputs will be received through multiple dendrites. These are dendrites are called input zone. So in this case, we are having input vector. Okay, now x1 to x1, x2 till xn, we are having an input vector. So these input vector will be nothing but it's a dendrites. Okay, now so input versus dendrite, clear? Okay, now at the same time, the synapse, we are having synapse. So synapse versus weights. So synapse, and we are having this weights. Okay, so synapse control the strength of signal between neuron and adapt through the learning. Synapse is a junction. It basically controls the amount of information that has been passed from another neuron. Okay, and that will be controlled by synapse. Okay, but in this case, that will be controlled by weights. So in each node, so this input will pass to a node. That node will be having some weights. Okay, this another input will pass to another node. It will be having some weights. Then this input will pass to another node. It will be having some weights. Okay, so these weights will be replica of synapse. Now we have this summing zone. We call it a summation, sum function. That summing zone is nothing but it's a basically cell body or soma. So what it does, it basically multiplies this x1 to w1 and passes to summing zone. It multiplies x2 to w2, passes summing zone, xn to wn passes summing zone. This summing zone will add all the information, that is x1 y1 plus x2 y2 plus xn yn, and it will sum. It will be basically input value multiplied to its weight. Okay, input value multiplied to its weight, input value multiplied to its weight. All the result has been summarized or has been summed in the summing zone. Now this summing zone pass this information to activation function. So activation function is nothing but it's our axon heliops, that is firing decision. Okay, it basically fires the decision. Okay, or we can call it a output threshold. If the sum of information passes some output threshold, then the neuron will be activated and it will pass the signal. In this case, if the sum of this information passes the threshold, or we call it activation function, if the function activates with this input, then the output will be fired. So this is the replica of human neuron. Okay, and it's our artificial neuron. It is clear? Now let's look at the anatomy of artificial neuron. So it is the basic artificial neuron. Okay, so what we are having, we are having input signals. So input signals will be this will be your input information. Now let us say if you are passing some image having 25 cross 25 pixels, then the number of pixel will be, let us assume it will be 25 cross 25. Okay, so all the values will be passed here. Okay, now these are the first pixel will go to the x1, second pixel will go to the x2, and last pixel value will go to the xn. So the input signal is nothing but it's the raw information that we are providing. Okay, if we are providing 1,000 raw information, the number of inputs will be from x1 to xn. Okay, and it's a vector representation. Okay, the x1 will pass. Now these are nodes. Okay, these nodes are having weights. It is called learnable parameter. Now, why we call it a learnable parameter? Because initially when we design or we will create a neuron, then the weights will be randomly assigned. Okay, or it may be, let's say it will be initialized to 0 or something else. Okay, so either it will be, most of the cases it will be randomly assigned. Okay, so we have to update this weight based on our output, because what we are doing, we are passing the information. Now let us take, we are passing the board image. Okay, in board images we are passing the board image, the information will be pixel values. So pixel value will be passed in from x1 to xn, and the output will be the probability of board. So the probability of board must be 1. Okay, so based on initial learning, this weights will be updated. Initially the weights will be random, it will try to predict the board information. Then the board probability and actual probability, it will find the error. Okay, that error will be back propagated and it will be adjusted in this weights. This weights will be adjusted in a such a way that the value will be updated, this w1 to wn, in a such a way then when you will pass a board image, it must give probability for board as a 1, or it will give board probability as a highest. Okay, so how these are input signals, these are some weights. Now these are the, basically these are the summation function, where it is summing the w1 x1, w2 x2, wn xn. It is summing all the multiplication of input to the learnable parameters, and that sum, it will be represented as a summation of wi xi plus a bias. We add a bias, we will understand why we need a bias. Okay, okay, that bias will be there. Okay, this value, this total value will pass to a activation function. In this case, in our case, it will be a axon in a new normal neuron. Okay, so it will pass to a activation function. Activation function in deep learning, the most of the activation function will be non-linear function. Okay, so the function will be passed to a non-linear function. That non-linear function will try to map this to in another value in terms of a probability or in terms of a classification output, and then output will be fired. Now we need to try to understand what are the input distance. The input signals, basically this represents the raw data, or it can be features also, or it can be single signals directly entering from the some type of a ECG device or any other handheld devices directly to the neuron. Okay, then this w1, w2, and these are learnable parameters. These are weights that will be controlled, or these weights basically influence the decision of this entire neuron. Okay, these weights will be updated during the training process. Okay, then we have this summation function that will try to sum up all the basically weights of multiplication of inputs and weights. So basically it gives the what we say, this weights basically gives the importance of the input signal. Okay, whatever input signal, how much importance will be here, this weights assign that, try to give that importance of each input signals. Okay, then we have this bias. Why do you need bias? Basically, so bias are some value that we added to this some value here, so that the output of this activation function should not be 0. It will give you some output. If in some cases what happens, the summation of this everything, this w1 x1 to wn xn, it will become 0. If the neuron is basically the summation is 0, then neuron will die. So to avoid the dying neuron phenomena, we add a bias so that neuron will be active. Okay, that is the major responsibility of a bias. Okay, it ensures that even when all the inputs are 0, the neurons can still output a signal, whether the signal will be in positive, or it can be a probability, or it can be a negative output. Okay, it will try to give the output if all the signals are 0 also, so that neuron won't die. Okay, and this output signal is nothing but the output can be numerical value if it's a classification task, or it can be a probabilistic value if it's a regression task. So in regression task, it will give you the continuous information, whereas in classification task, it will give you discrete information. Okay, now let's go to let's see how actually this neuron works. So we have already seen, okay, this is called MP neuron. Okay, McLeod-Pitt neuron. This is the backbone of all the deep learning model. Okay, so what happens? We will try to predict output. Basically, if neuron gives output, then value will be 1. If it is not giving any output, then the output will be 0. So basically, it's a binary decision system. Okay, so in binary decision system, we will give some input to the neurons, input to our MP neuron, and we will try to find the output. Okay, now it's a basically binary output. If neuron fires, then output will be considered as a 1. If neuron is not firing, then output will be considered as a 0. So basically look at here, if all the information is 0, so it is continuously 0. If it passes the threshold value, there will be some threshold value. So that threshold value is this theta. If the summation of this information passes to theta, we will pass this sum and this both, okay, to this as an activation function. Okay, if this summation passes this theta, it means the value of the sum is more than or equal to the theta, then neuron will fire. Otherwise, it won't fire. Okay, that is a basic principle that has been known as a MP neuron. Okay, and it's a backbone of artificial neural network. So, if the, let's say u is an input number, okay, if u passes the threshold, then output will be 1. If u is not passing the threshold, then output will be 0. And u is what? It's nothing but it's this summation. Okay, u is nothing but the sum. U equals to summation of I equals to 1 to n wi xi. So u is the summation of all the input signal with respect to their weight values. Okay, now let's take a working example. Now we have taken inputs as x1, x2 and weights w1, w2. So let us assume that weight value is 1 and 1. Okay, and threshold we have decided as a 1.5. Okay, now what happens? Initially it will be the value of x1 and x2 we will decide. So these are, let us consider as a binary implementation. So x1, x2 can have 4 different values. Both of x1 and x2 can have 0. It can have 0, 1. It can have 1, 0. It can have 1, 1. Now let's say if both are 0, then it will be w 0 into 1 plus 0 into 1. It will be 0. So 0 is less than 1.5. Then output will be 0. Okay, look at here again. Let's say it's 0 and 1. The value will be 0. Okay. First, so 0 into 1, it will be 0. 1 into 1, it will be 1. So it will be 1. So 1 is less than 1.5, so output will be 0. In next case, it is 1, 0. Okay, so in 1, 0, what happens? 1 into 1, it will be 1. 0 into 1, it will be 0. So 1 plus 0, it will be 1. Less than 1, 1.5, so it will be 0. Okay, now let's say we are taking 1, 1 for both. So it will be 1 into 1, 1. 1 into 1, 1. So 1 plus 1, 2. The 2 is greater than equals to 1.5, so the output will fire. Okay, now can you tell me what this basically represents? So it's just a basic working example of a AND gate through a MP neuron. We have implemented AND gate in MP neuron. Okay, where the input is not binary input. Okay, and the summation will be, this threshold value is deciding where the output will be 0 or 1. Look at here, if we are having both 1, then only we are getting 1. And in all the cases, it is 0. Okay, now let's take another example, and we have already seen. Okay, now let's take OR example. We have to implement, let's say, OR gate. Okay, so we know, all of you know what is OR gate. So let's say we have to decide the threshold as a 0.5. Okay, you can update threshold, and you can update the weight value also. In this case, we have fixed w1, w2. We will see how to update the weight value also. Okay, now the x1, x2 and threshold is 0.5. Now let's assume it's 0, then it will be 0 into 1 plus 0 into 1. It will be 0, 0. Output will be 0. Now if x1 is 1 and x2 is 0, it will be 1 into 1 plus 0 into 1. It will be 1. So 0, 1. It is giving 1, which is more than threshold, so it is firing. Output will be 1. If the reverse case, it is 1, it is 0. In that case also, the summation value will be 1, and it will fire the neuron, since the 1 is more than threshold value. It is fire. Okay, and if both are 1, then the output, again, the total sum will be 2. Okay, and it will fire the neuron. The output will be 1. So look at here, whenever we are having at least 1, either in x1 or x2, it is firing. The neuron is firing as a giving output as a 1. So it is basically replicating OR gate using MP neuron. Okay, so this McLuch-Pitt neuron is the first mathematical model of computation. Okay, it performs threshold logic with a binary output, and that can implement fundamental logic gates like AND OR. Okay, but it can implement only AND or OR, or in some cases not. But it can't implement XOR or XNOR type of gate. Okay, due to the linear separability. Okay, let us see. Now let's see what is a perceptron model. It was a MP McLuch-Pitt model. Then this MP model or MP neuron has been improvised to create perceptron model, and this perceptron is a backbone of ANN. In ANN, we are using perceptron model. Okay, so what is a perceptron? Basically, a perceptron is the simplest type of artificial neural network. Okay, it is a single layer feed forward model used in binary classification. Okay, now In that case, we were using threshold. Now we will use bias. What are the key characteristics of this perceptron model? In this case, it's a single layer. It will having no hidden layer. Then it gives you a linear decision boundary. Okay, either it will give 0 or 1. Binary output will be there, and it works on a supervised learning. Okay, now it's the same. We are computing V. Okay, so V is nothing but it's a summation of I to 1 n wi xi plus a bias. We are adding a bias term. We have already seen why we need to add bias. Okay, so that if all the inputs are 0, still there will be some output in terms of a 0 or 1. Okay, so that the dying neuron phenomena will be reduced. Okay, and that activation function, we are having this activation function. It's a function over V. F of V, the value of y will be 1 or 0. If the value is f of V, because this V will be given as an input to this function. Okay, if the value of V is greater than equals to 0, then it will output as a 1. If its a value is less than 0, then the output will be 0. This is a simple perceptron model. And the architecture is this. We are having input weights. Okay, we are having input signals or input information. We are having weights. We are having one bias. Okay, here the value will be 1 because the bias value will be B. So 1 into B will be B. Then we are having a summing unit, and we are having an activation function. So this is a basic perceptron model. Okay, now let's try to mimic the learning process, how the learning process works actually. So perceptron models learns by adjusting its weights and bias to minimize the error between predicted output. So look at here, what it does, it will try to predict the output. In some cases, it has to predict the output at a 0, but it will predict it as a 1. Okay, in some cases, it will predict the output as a 1, but actually that output should have been 0. So based on this predicted output, it will try to adjust this weights as well as this bias information. It will adjust this because input information we can't change. Okay, so what we can change, we can update this weight value in such a way that our model will be more accurate. Okay, now let's see how it is done. So basically, first we need to try to predict the output y. Okay, so based on that predicted output and actual output information, that is called target output. Okay, so actual output is target output. So it's a supervised learning now, because we need actual output. Then only we can perform the learning. Okay, so it will, based on these two information, it will do the training. It will update the weights. We will see how it will update. Okay, so and basically the process is to minimize the error. Okay, now the working principle is initialize the W and bias to a small random values. Okay, so we are having this x1 to xn. These are fixed input information that will be given as an input. Then this w1 to wn and this bias, we will randomly initialize it to a smaller values. Okay, now once these has been initialized, in second, for each training example, we have to compute the output y. Let's say if we have taken the first training example, we will, for first training example, with a random weights that has been initialized, it will try to predict the output. Okay, once output has been predicted, if the output is correct, okay, whatever output we have received in y is basically output function. It's a basically output. Okay, and t is what? Your target output. If it matches, okay, then there will be no change. If it doesn't matches, then there will be updation. Okay, if prediction is incorrect, so we have to update both our output, our weights as well as our bias, and we have to repeat this until all the training examples are classified correctly. Okay, or maximum epoch achieved. Okay, in case of if let's say if you are running for a 30 epochs means, let's say if you are having 1000 training samples, then you have to run that 1000 training samples for 30 times. Okay, so 1 epochs means training your entire model with all training samples. Okay, so until this maximum epoch reached, or you have completed with all the training examples. So we have to repeat this process. Okay, now what it does during this process, it try to create a linear decision boundary, that perceptron model. Okay, so let's say if we are having 2 classes, then it will try to fit a line. Okay, it will try to predict a line, so that if something falls just after this line, so it will be class 1. Within this line, it will be class 0. So why? It's a line because look at here, it will be w1 x1 plus w2 x2 plus wn xn plus bias. It should be greater than some threshold. Okay, So look at here, it is W1x1 plus W2x2 plus W1xn plus bias, it should be equals to 0. Okay, or in some cases greater, it should be greater than less than some value. So this is a equation line. Okay, with a, it's a basically multiple variable dependent equation, line equation. Okay, so we have to basically try to find this boundary. Okay, how perceptron algorithm works? It will initialize the weights and biases to a smaller value. Okay, for each training example. So training example is this X is our input information, this T is our target information. So these are input signal from X1 to Xn, and T is our target information. So for each sample, okay, for each sample, it will compute the net input, that is V. It is net input, it is nothing but it's a summation of all the inputs with their with multiplication of their weights and in addition to the bias. Okay, and it will try to compute the output, that Y. Okay, now if Y is, there will be no update. If it is not, then there will be update, and this process will be repeated unless until the convergence will be there. It means there will be no error or your maximum epochs will be reached. Now how weight updation will be performed? Look at here how weight updation will be performed. We are having W new, it's a new weight. W2, it's an old weight. Now in this case, is W1, it is old weight, and W1 dash will be a new weight. So new weight and old weight. Okay, now we have this eta. This eta is nothing but it's a learning rate. It's the amount through which your weight will be adjusted, and we will try to keep it a minimum value. It's the learning rate should be between 0 to 1. We will keep it a lower value so that the learning rate will be slow. Okay, if we keep a if we use a larger value in eta, the learning will, this eta is a learning parameter, it will use in all deep learning architectures. Okay, if the learning parameter, we in deep learning cases we just try to set it into 0.001. Okay, so we try to keep it a very smaller value so that learning will be slow. Okay, if the learning parameter is high, then there will be fast weight update, and there is a chance that your model will be underfit. Okay, so to get a new weight, we need to write the old weight plus eta. This T is your target minus Y is your predicted output into X. Okay, and the new bias is B new equals to B old. It was old bias plus eta into T minus Y. Okay, so let's say if you are our old weight was, let us assume 0.5. Okay, so let's say it's 0.5. Okay, and let's say your eta was 0.01. So let us assume that eta is 0.01. Target was 1. Okay, and let's say our predicted value was 0. Okay, so it will be 1 minus 0, it will be 1. Eta will be 0.01, and X will be, let us assume that X is 1. So it will be 1 into 0.01. Okay, it will 0.01 plus W old was, you know, weight, let's say W old was 0.5. So it will be 0.51. Your new weight will be there. Okay, now let us assume this beta new, bias new. Let us say that old bias was 0.2. Okay, so it will be eta is our 0.1. Okay, it is 1, it is 0. So old bias will be 0.5 plus again 0.1, it will be 0.6. Okay, in this way, the weights will be updated in a perceptron model. This is the basic learning flow chart of your working of a perceptron model. Okay, you can see here. These are just update rule. The updation rule are these two. Okay, now again, the perceptron model can implement linear decision boundary. It cannot implement the complex decision boundaries. So all the linearly separable problems such as and or not problems, it can be implemented through perceptron models. Now, limitation of perceptron models, it can work on linearly separable data. It is solvable if the data is not linearly separable. In this case, look at here, the decision boundary must be like this. Here to here, it should be like a star shape. Okay, it is not linearly separable. In this case, perceptron won't work. Okay, now in case of a XOR problem, you know, it's exclusive OR. So it's a classic example of non-linearly separable problem. So this XOR problem cannot be solved by a straightforward perceptron model, because if 0 is 0, it will be 0. If 1 and 1, it will be. If the input signals are same, output will be 0. If the input signals are different, output will be 1. So that's why it cannot linearly separate. Okay, so this is why XOR problem, this perceptron model fails in XOR problem. Now, let's see the different activation function that we are going to use in our deep learning architecture. The first activation function. So activation function is a mean function which will decide what output will be generated from your neuron. Okay, so squashes the input to 0 to 1. Okay, it's a sigmoid function. Look at here, it's a basically defined like it's a 1 by 1 plus e power minus z. Okay, these minus z is your threshold value. Okay, now its derivative is also used. So this is the plot. If your value is up to threshold value, then it will be map here. Otherwise, it will map here. This z is your input. Okay, if your input value are negative, then it will map up to 0.5. If your value is positive, then it will go from 0.5 to 1. The output will be in between 0 to 1 only, whether your input is negative or positive. Okay, so it will try to map the output into 0 to 1. So whenever you have to predict a continuous value or you have to perform regression task, okay, we will go for a sigmoid activation function. Okay, whatever input you are having, it will map it to 0 to 1. Now, what are the key properties? It is smooth and differentiable everywhere. Okay, not zero centered. Okay, it is not centered around 0. Okay, can suffer from vanishing gradient for large. We will discuss what is a vanishing gradient, okay, later. It is used in output layer for binary classification. Basically, it will predict the probability between 0 to 1. If the probability of some class is high, then the output will be for that class. So it is best for binary classification and avoid in hidden layers. We generally don't use in hidden layers, but the recent networks, that LSTM models, also uses this sigmoid function in hidden layer. Okay, we have then we have this tanh. We can call it a hyperbolic tangent also. It squares input between -1 to 1. Okay, if your input, look at here, this z is the input value. Okay, if your input is up to 0, then output will be -0. Up to minus, it will be in between. If your negative value is whatever negative value you are having, okay, if you are having a negative value, then output will be between 0 to -1. If you are having positive value, then output will be between 0 to 1. Okay, so basically the function is e power z minus e power minus z divided by e power z plus e power minus z. Okay, z is your point. Okay, look at here, z is our input signal here. Whatever input information, that actual v value that we are calculating in our summing, that is summation of wi xi plus bias, that is z. Okay, so we will pass here. Okay, if the value is negative, so it will map it between -1 to 0. If the value is positive, it will map it to 0 to 1. Okay, it is centered around 0. Smooth, differential everywhere. Okay, less prone to vanishing gradient than sigmoid. Okay, because the mapping range is higher. Here the mapping range is 0 to 1. Here mapping is -1 to 1. Okay, it can be used in a hidden layer also. LSTM, that is long short-term memory, also uses this tanh function. Now this is ReLU, that is rectify linear unit. Okay, this is a non-linear function. This ReLU is the key activation function of a deep learning or CNN architecture. So what ReLU does, it maps the input information between 0 to infinite. If the z value, that is your summation value, that value is positive, the output will be same. If the z value is negative, then output will be 0. Okay, so whatever z is nothing but it is this, the calculated value. This is z. Okay, this sum, it is z. Okay, this z value, okay, that z value is positive, then output will be the same. There will be no change in the output. If the z value is negative, then the output will be 0. Okay, now output will be in between 0 to infinite. It's a very simple and efficient, helps mitigating vanishing gradient problem because the range has been now increased. The mapping range is now 0 to infinite. In this case, the mapping range is just between 0 to 1. Okay, it is not centered around 0 and can cause dying ReLU. Now dying ReLU, in what is dying ReLU? So in some cases, if the output is continuous in some neuron output that we are getting, that sum we are getting is continuously negative, then the neuron will be that the firing value, that output of this activation function will be 0. Okay, so there is a chance that in some cases, many neurons will be always producing 0 as output due to this negative summation. Okay, so the neuron won't fire. Okay, that is called dying ReLU. To avoid this, we have two more ReLU version, that is called leaky ReLU, and there is one more ReLU version. Okay, then we are having softmax function. This softmax function is basically key of classification. it is always used in the last layer of your output, where you will try to predict the classification. Okay, so basically it's nothing but it's a EZI, where ZI is your that summation, okay, and sum of all ZIs, and it will try to predict the probability. Okay, so probably it will compute the probability. It will be between 0 to 1. If all the outputs are between 0 to 1, then summation, it should be such a it should be in such a way that the output, sum of the output will be 1 for all the output cases. Let us suppose we are having 4 classes, then the for class 1, class 2, class 3, class 4, it will be class 1, 2, 3, 4. Okay, the total probability sum will be 1. Okay, so these are some activation function that we often use in our deep learning architectures. Okay, now we have already seen how forward propagation works. Okay, so we have already seen this activation function will be there. Now in first layer, now look at here, input will be here, input will pass to one hidden layer. So one hidden layer will be what? It will be basically, it will be collection of a summing unit and an activation function. Okay, based on that, it will generate one output. Okay, so all x1 to xn with a bias. So all nodes will be having separate bias. Okay, it is having another bias, it is having another bias, it is having another bias. Okay, so based on that, it will calculate the summation of xi to wi, and the bias will be added. Will be summing unit plus activation function. It is summing unit activation function. It is summing unit activation function. This is the first layer. Then output of this layer will be fed to another layer. Then output of this layer will be fed to another layer, and it's the last layer. In last layer, we will be using that sigmoid softmax function. So softmax function will be, we are having multiple information 1, 2, 3, and we are having multiple this. So based on that, we will first try to find the sum value. Then we will use that sum value in this function to find out the probability. And the value, the unit that is let's say class having highest probability will be given as a output. So this is called forward propagation, where that information will be propagated in forward direction. Okay, now we are in case of ANN, we used to try to find the loss function, because whatever probability we are getting here now, so during training it will be feed forward. Okay, but there will be error. So during training we will be having one target value. Based on that target value, we have to update this. That is called back propagation. We will backly propagate whatever the loss function, whatever the loss will be there. Loss, it means the difference between predicted value and the actual value. Okay, that will be loss. That loss, the derivative of that loss will be propagated in backward direction, so that the weights between these hidden layers can be updated in such a way that it will give the actual and correct output. Okay, so we are having a loss function. So basically loss function will govern the entire updation process, and our target is to optimize this loss value. The loss should be minimum. So the loss function is, we are using two type of loss function. One is called MSE. If you are using regression task, then we will go for MSE. If you are using a classification task, then we will go for a cross entropy. Okay, so regression task formula, it is clear. Wi is your actual value, it is predicted value, then summation of these with a square. Okay, so it is a loss function. In case of a classification problem, the loss function is y log y dash plus 1 minus y log 1 minus y dash. It's for binary. It's a binary cross entropy. If we are having multiple classes, then the cross entropy will be this summation of 1 to k minus, where k is a number of classes. It is a negation of yi log yi dash, where yi is a predicted your actual value, and y dash is your predicted value. So based on that, we will calculate the loss, and our target is to minimize the loss. Okay, due to some y value, the loss will be minimum. So since loss will be minimum, your output, that is accuracy or your precision, will be maximum. Okay, so our target is to minimize the loss. So we can use MSE for a regression task, and we can use cross entropy for the classification task. Okay, now let's say, for example, let's take a binary classification task. We are having a true label as a 1. Okay, now let's say prediction 1 as a y dash and y dash. Okay, these are two prediction, because for two classes it will predict, class 1, class 2. Okay, so class 1, it is 0.9 prediction, correct and confident, and it is 0.1 wrong and confident. Okay, in both cases, let us try. The MSE was, it will be 1 by 2, 0.9 minus 1 whole square. It will be 0.005. In this case, it will be 0.405. Look at here. It was a wrong and confident, but it was a wrong, na? so the loss is very high. Okay, but it was a correct prediction, so loss is very low. Okay, and during back propagation, when we are going to update the weights, the derivative of this loss will be used. Okay, now in cross entropy, look at here, it will be log 9, it will be log 0.1. In both cases, it is having more loss. Look at here, if the prediction is wrong, then loss is high. If the prediction is correct, loss is 0. Loss is near to 0. So our target is to minimize the loss. Loss cannot be 0. We have to minimize it. Okay. Now let's see what is a gradient descent. It's a basically optimization function that our ANN uses. It is called gradient descent. Okay, so gradient descent is an optimization algorithm that minimizes the cost function. The optimization you must know, it's basically a target to minimize or maximize something. In our cases, we have to minimize the loss function. For classification task, it will be a cross entropy, or for a regression task, it will be a MSE. Okay, for both, we have to minimize it. So it's a gradient descent is algorithm that will minimize the loss. Okay, so how it does actually? So basically, when look at here, first we need to understand how that gradient descent works. Okay, it will initialize a parameter theta randomly small values. Okay, now this theta nu, we have to compute j theta, that is current parameter. This j is a Jacob matrix. Okay, then compute gradient of this. Then we update the parameter, that theta nu. Theta is your weight values, na? Okay, theta nu minus equals to theta old minus eta and this gradient of j old. Okay, this eta is learning parameter. It should be minimum. Okay, we have seen the learning parameters affect while weight updation when we were seeing perceptron. Okay, so we have to repeat this process until this cost, that our whatever cost it is, that lost function, the value will be less than some pre-decided value. Okay, that is the gradient descent approach. So what happens? This is j theta value. It will be like a bell structure. Up for some theta, it will go somewhere and it will achieve a minimum. When you change it, there will be a chance that the cost will be increased. So we have to optimize this value. We have to find this minimum point. Okay, so for that we need to decide some stopping criteria. The stopping criteria, there are different stopping criteria. Based on that, this optimization function can stop. And this threshold value will be very smaller. It will be like 10 to power minus 6. Okay, now look at here, when we keep eta too small, it means that learning parameter is too small, then gradually it will reach to this bottom. Okay, it will take very long time. Okay, very slow learning. If it's a good eta, so there will be faster convergence. It will reach to the optimized value faster. Okay, but if you are taking too large eta value, then it will toggle. Sometimes it will go here, then trajectory here, then it will toggle like this. Okay, so we have to find this good eta value. It's basically a hyperparameter. Okay, where we literally for deep learning architecture, you have to pass this eta value. Okay, this is the basically optimization technique that our deep learning architectures, or deep learning architecture mostly use stochastic gradient descent. It's another version of this gradient descent. So it is a basic principle behind the optimization that done in and that updation will be basically, it's a back propagation. We will optimize this cost. Okay, we have back propagation. Okay, now this training process, look at the training process of a deep learning architecture. Initially we will initialize the weight. So these are weights. The random values will be initialized to all the this neurons. These are input signals. Okay, and these are having weights. Okay, all this connection will be having weights. So we will initialize it with the random values, and the bias will be initialized with a smaller random values. Then the forward propagation will does. Okay, in forward propagation, for each input signal or each input sample, we will try to predict the output. Okay, y value. Then we will compute the loss function. Then based on loss function, we will back propagate the error. So it will be basically this. What happens? The gradient of this loss value. Okay, it will be propagated. Whatever j we are calculating here, now it's a loss function, so its gradient will be propagated backwards from this initial layers to the final last layers. Okay, these are called top layers to the bottom layers. This side called bottom layers, which are near to input, and which are near to output called top layers. From top layers to bottom layers in a backward direction. Now what happens when we are using sigmoid function? Then this loss function is propagating backward, na? So there is a chance that the gradient that propagating backwards will vanish sometime after some layers, the gradient will become 0, and there will be no updation in the initial layers. So that is called vanishing gradient. Gradient will vanish. There will be no updation in the starting layers. Okay, that is a very big challenge. That's why we use a ReLU function. Okay, then weights will be updated based on this gradient information, and this will be repeated until your epoch will reach, or there will be minimum number of minimum loss is achieved. Okay, so these are basic example of the basic training process. So basically initialize the weight, forward propagation, compute the loss, backward propagation for a adjusting the weights, then weight will be adjusted and it will report until all the epochs reached. Okay, now we have already seen these are hyperparameters in any deep learning model that we use to set. First one is known as learning rate. We already seen what is a learning rate. If learning rate is too small, then it will slow learn. The convergence will reach very slow. Okay, if trailing is good, then the convergence will be also reach faster. If the learning rate is high, then there will be a toggle. You won't be able to reach to the convergence. Okay, so typical guidelines for a typical value, it will be from 10 to the power minus 4 to 10 to the power minus 1. It means it will be from 0 to 0.1 to 0.0001. And mostly we start with the 0.001 and we will try to adjust it. Okay, and optimizers, we have a gradient descent, but deep learning architectures mostly used ADAM and RMS prop optimizers. These are another examples of optimizers. Okay, now epochs, the number of epochs are basically number of completes processed through the entire training data set. In your model will be entire training data set will be passed into your model for the training. That will be one epoch, and number of epochs will be multiple times it will be passed. Just second. So Sanjay ko de dena. Okay, so now it will be passed. Okay, now what happens when overfitting and underfitting will done? Okay, if your model is stopped here at this point, it is called underfitting. Okay, and when your model is here, it will be called overfitting. Okay, so what is underfitting, overfitting? Underfitting means your model will not achieve good accuracy in your training data as well. Okay, because losses is still decreasing. Okay, and overfitting is what? By reaching to the optimal point, your loss will again increase. What happens? Your model will perform very well in training data, but in testing or validation data, it will perform poorly. Okay, this is called epochs. Okay, now batch size basically batch size is the number of sample you pass in one batch. Okay, it's basically number of training sample used in one forward or backward pass. This is called batch size. And in one epoch, it means, let's say if you are having, let's say 128 images, the batch size is 16, the number of passes will be 16 divided by 128. In that number of passes, your one epoch will be completed. Okay, so batch size is nothing but it's a number of training sample we used in forward and backward pass. Okay, if the batch size is very small, then the updates will be very noisy. If batch size is larger, then the update will be smoother and faster convergence will be there. So we will keep in batch size like 16, 32, 64, 128 to 56. Okay, now the number of hidden neurons. So it will be basically, it depends. If number of neurons is very few, then it will be underfitting. Your model won't train. It won't learn the pattern. If too many neurons are there, then it will overfit. It will try to learn the noise also. Okay. Now, if the number of neurons are good, then it will learn the pattern. So these are some common hyperparameters that we use to tune in the deep learning architecture. One is learning rate, epoch, batch size, and number of hidden neurons. Okay. Now let's understand between overfitting and underfitting. So these are two common terms which often comes in deep learning: overfitting and underfitting. So basically, target of machine learning is what? It has to train on a known data and it has to generalize well on a unseen data. It is our target. It means we will learn on a known data. It will have having labels, and that same learning, whatever we have learned, we will try to predict in unknown data. That is the major motivation behind machine learning. Overfitting and underfitting are two common problems that prevent this model achieving this goal. That is basically generalization of a model, working a model better in unseen data. That won't achieve due to these two problems. That is called overfitting and underfitting. Now, what is a Basically, what is a overfitting? Overfitting, it means your model try to learn the noise as well. It means for a training sample, your model will work too well. It will try to predict everything. Okay, it includes the noise, random fluctuations also. It will perform very well on a training data. But when you will test it in a very let's say testing data or unseen data, it will fail. It will perform miserably. So that is called low bias. Low bias means it will low bias means training error. So training error will be very low. High variance means the testing loss will be high. So low bias means it will achieve lowest bias for the training, but the loss will be more for a testing sample. That is, if variance is high, bias is a low, then this is called overfitting. All of you know what is a low bias means? Training loss. Training loss will be minimum. High variance means testing loss will be high. So it is called overfitting. Look at here. It is literally try to learn the pattern of even noise also. This is called overfitting. Okay, it will learn everything. For example, if you want to classify a person and a boy or girl, it will try to differentiate between the boys also. Okay, it will try to learn pattern for every sample. That is called overfitting. Now, what is a underfitting? Underfitting is model is too simple. Your model is not even trying to understand the pattern, hidden pattern of data. Okay, it will performs very poor on your what we call it training samples. So it will perform poor on training samples, and it will perform poor on a the variance will be low. Okay, look at here. Data is too simple. This is underfitting. It is not trying to basically the problem was a not linear separable problem, but it is trying to separate it linearly. So this is called underfitting. Now, what is the cause of overfitting? First major cause is model complexity. If your model is too complex, it is having too many parameters, then it will be overfit. Okay, if you are having too many features, it will overfit. Training too many epochs, if the number of epochs is very high, then there is a chance that it will be overfit. If there is a no regularization, it will overfit. Solution is what? The first solution generally we go for to get more training data. First thing. Second, we will try to simplify the model. If we can't simplify the model, we will try to reduce the parameters. We use regularization, L1, L2 regularization. We will try to add dropout. We will discuss what it is. Dropout, what? Early stopping is what? Feature selection is what? We will try to do it. Then we will go for a data augmentation. So if your number of training sample is less, then we will go data augmentation to increase the sample size. Okay, these are some common solutions. Okay, for underfitting, the model is too simple. Okay, then if there is a very few features that has to learn, insufficient training information, if we are using very strong regularization technique, or we are using early stopping too early, now if it means we are not training for a sufficient number of epochs. So these are the causes why this model go for a underfitting. Okay, now solution is use complex model, add more relevant features. We have to train on more epochs. We have to reduce the regularization. Okay, these are penalty terms. Okay, feature engineering we need to collect more data. So these are common ways to remove the underfitting. So look at here the comparison: underfitting, overfitting, and good. Look at here, model complexity too simple, too complex. It will be just right in good fit. Training error high. Training error will be very low in overfitting. It will be low. Testing very high error. It will be very high. It will low. Bias high, low, low in both cases. Variance low, high, low. Generalization poor, poor. It will be good. So we have to find this good fit. Okay. Now the 7 strategies basically. These are the regularization. First one is a dropout. So first we need to know what is a dropout. So the dropout is basically we are having this neurons now. So randomly we will try to drop some neurons. So why we need to drop some neurons? So that number of parameters will be reduced. That is called dropout. Okay. Now then we use for pulling layers. Okay. In pulling layers, what happens? We will go for a max pulling. We will go for an average pulling. Okay. Then we are going batch normalization. So basically, what is a batch normalization? So in batch normalization, what happens? It computes batches in batches mean. Batches means number of batch we are passing, na? 16, 32, 16 number of sample we are passing in one pass. Okay, that is called batch. So we are trying to compute the mean of batch. We are trying to compute the variance of batch. Then we will normalize the input. That is called batch normalization. Okay, we will try to normalize the values. Okay, and we will scale and shift the normalized values. That is called batch normalization. Then we will go for a pooling layer. So pooling layer basically it reduces the complexity, or it reduces the feature map size. We will see what it is. We are having max pooling, mean pooling, average pooling, or global pooling. That we will go for a pooling layers. We will perform early stopping. Okay, so early stopping it means, let's say if you have decided to run your model for 30 epochs and you are that lowest by let's say your loss is not increasing for 5 epochs, then you can stop. So we have to put some criteria for early stopping. If there is a no change in loss, if there is no change in accuracy, okay, in that case we will try to do the early stopping. Okay, then another is injection of a noise. Okay, we will try to add noise in input images. Okay, so that it can learn the noise pattern. Okay, it can try to basically avoid this overfitting. Then we are having L2 and L1 normalization. These two are regularization technique, L1 and L2. Basically, where it adds penalty terms to the loss function so that the weight will be not drastically updated. Okay, or at last we can go for a data augmentation. In data augmentation is what we will try to, let's say we will try to basically get more samples from the same data by performing augmentation. Augmentation means generating the data, multiple data from same data. Let's say for by doing scaling, okay, we can scale up, scale down, okay, zoom up, zoom out, zoom down. Okay, we can flip the image in vertical flip, in horizontal flip. We can rotate the image. We can inject some noise. We can do some occultation. These are some techniques where data augmentation can be done. Okay, so these are 7 strategies to mitigate the overfitting in CNN. Okay, now these are the limitation and application we have already seen. Okay, now let's move to the CNN portion. That was a deep learning architecture. Now in CNN, we will basically see the introduction to CNN, fundamental CNN architectures. Okay, then some biological inspiration, and then we will go for the evaluation of CNN also. Now let's try to understand what is a CNN basically. So CNN is nothing but it's a chain like or sequential structure. Now right now we are not using sequential structure also, we are using parallel CNN also. Okay, so we are taking an input image, we were performing some CNN basically stands for convolutional neural network. So this convolutional word, it's a basically an operation that we has to perform. So we will do some convolutional, then we will go for a pooling, then we will go for a fully connected layer, then there will be output. Okay, so basically a CNN composed of 3 basic layers: convolutional layers, pooling layers, and fully connected layers. And we are having 2 more layers, that is input layer and output layer. Okay, these are what just an example. Okay, now what CNN is basically, CNN is it's a basically specialized deep learning architecture designed to automatically learn and extract spatial features. Now till now we have not extracted a spatial features. In ANN it was just trying to learn the pattern. Okay, now we will try to extract the feature. We will see how to extract feature. Okay, so basically in CNN we will do 2 things. Initially, or to this portion, this convolution and pooling portion, we will do feature engineering. Whatever information we will get, we will try to extract the feature, and then at last we will try to classify that feature or regress. We will perform regression also. Okay, so our task is to divide the CNN into 2 parts. One is feature engineering and another one is a classification, okay, or regression. Okay, so that's why CNN works very well for image as well as video. So CNN are highly effective for image classification, object detection, face recognition, medical image analysis, video processing. Okay, why? Because it can extract feature automatically, it can share the parameters, the connectivity is sparse, translation invariance also, and it learns hierarchically. Okay, these are some key features. Okay, now let's try to understand the CNN. Okay, now why we need CNN? We were having ANN, na? So why we need CNN? The major problem with ANN is a number of parameters in ANN. Now let us assume that we are having 256 cross 256 RGB image. So we will be having 256 cross 256 pixel in one channel. There will be 3 channels. The number of input value per one ANN will be 1,96,608. Okay, now let us say in input, let's say in first layer we are using 100 input, 1000 input neurons. Okay, or let's say it's an input layer. Now we are having this many inputs values. So x1 will be 1 or xn will be 1,96,608. So that many inputs are there. Okay, now what happens if in the first hidden layer we are having 1000 neurons? That there will be total this many connections will be there. 1,96,608 into 1000 connection will be there, because look at here. everything will be connected to each other na, in ANN. Look at here, all input has been connected to all hidden layers. Look at here, we are having 1,96,000 input in values, and here we are having 1,000 neurons. Okay, so it will be connected. So there will be 1,96,000 into 1,000. Okay, that is the major problem. Okay, then the value will be 1,96 million. So these are parameters. These are number of weights that we have to update. Okay, and updating this many weights, it is very difficult. Okay, that's why ANN has been absolute. Okay, it's very computationally high. Loss of spatial information is there. If this many parameters are there, then there will be overfitting issue. So there is so many problems associated with ANN. That's why we go for a CNN. Now let's try to look at the biological inspiration of a CNN. How biological works, our receptor works. We are having retina. Now we are capturing an image. Okay, so in image, this is retina. Retina captures the optical input. Then we have this LGN. So LGN basically stands for the lateral gynoculate nucleus. Okay, we are having two LGN, one for right eye, one for left eye, and left retina, right retina. Okay, this LGN information will pass the information to receptors of this cortex. So we are having 4 cortex, visual cortex 1, 2, 3, 4. Okay, and this cortex will now analyze the image and try to learn the pattern. The same way, it's a hierarchical representation. Na? From one layer to another layer, it is passing the information so that our brain can learn the pattern of our image. Okay, in same way, this CNN works. CNN is having a dense, look at here, input, it is input. Okay, optical input is there. It will pass to a convolutional layer. There will be some feature extraction like LGN. Then it will pass to the pulling layers like this virtual cortex. Then it will be flattened and there will be output. It's a basically prediction layer. And this flattened or dense layer will be basically, it will be like artificial neuron. All the neurons will be connected to each other. Okay, so it's a hierarchical representation. So we are having multiple convolutional layers. Now, why multiple convolutional layer? The layers that are near to this optical input will detect edges and lines. It will detect smaller features or local features. Okay, mid layers, it means if we are going for a, let's say 100 convolutional layers, let's say in 40th layer, it will learn the textural patterns. Okay, and in 100th type of layer that we call deep layers, it will learn the complex objects, that it's a dog actually. Okay, that's why we call it deep learning. The number of layers is very deep and it will learn from in reverse direction, from deep to shallow. Okay, so basically we are having 3 kinds of layers. Early layers detects edges and lines. Middle layers detects textures and pattern. Deep layers detects complex objects. Okay, now let's say this is the basically evolution of a convolutional neural network. In 1958, we are introduced with a perceptron. 80s, we have backpropagation algorithm to update the weights of perceptron. Then in 1998, we have LeNet, that is first convolutional net type of neural network. Then we have AlexNet. Then in 2014, there is a VGGNet, visual geometry group. This is a very effective for image processing. Okay, then we have in 2014 we have GoogleNet. 15 ResNet is there. In 19 we have EfficientNet, and in present day we are working on a vision transformers. So why it is the evolution of CNN is like this, because the GPU acceleration is there, improved optimization algorithms also going on. Okay, data is also enormously increasing. So these are some common reasons why CNN has been evaluated as evolved, and these are the basic CNN perceptron to vision transformer. Okay, now let's see the core idea behind the CNN. So basically in CNN, this is a basic CNN pipeline where we are having an input image. Now in case of CNN, the input size will be fixed. Okay, whatever input image you are taking, the number of number of neurons in input layer, a number of nodes in input layer will be fixed for all CNN architecture. Okay, we have to map it. Okay, so convolution, once input has been there, then there will be convolutional layer. In each convolutional layer, there will be activation function. Then activation function, after that, we are having pulling layer, then we are having fully connected layer, then we are having output prediction. So basically we will do some take input, then we will perform some convolution, we will use activation function, then we will use some pulling, then we will go for a fully connected layer, and then go for the prediction. So these are just basic pipeline of a CNN. So early layers detects local features, mid-level layers detects textures, shapes, patterns, and high-level layers detect, these are the high-level layers, this detects the semantic information like object, faces, abnormalities. Okay, these are the core idea behind CNN. Okay, now overall CNN. So I have already discussed this. So we have divided into three parts: feature extraction to extract the feature reduction. We will use pooling layers to reduce the dimensionality while preserving the important information. Okay, then classification. So the overall CNN architecture has been divided into three parts. Okay, now let's see the number of key components of CNN. We are having input layers, we are having convolutional layer, we are having ReLU, which is the activation function. Okay, rectified linear unit. We have already seen the definition of ReLU, how it works. Okay, for a negative information, it gives output as a 0, and for a positive information, it will keep the same value. Okay, we are having pooling layers, we are having max pooling, average pooling, and global pooling. We are having fully connected layers, and we are having softmax function. So these are key component of CNN. Okay, every CNN architecture made up of this. Okay, now let's try to understand the convolution first. Convolution block in a CNN, because the first thing is the convolution. After input, convolution layer is there. So input layer is what? It's a basically input. Whatever image will be there, that image will be reshaped into the input layer side. Now, for example, if you are using VGG16, then the input has been restricted to 224 cross 224 into number of channels. Okay, so we have to resize the image in such a way. Okay, now the first convolution block, a single convolution block will be made of one convolutional operation. This is called convolutional operation. We will see what it is, with one activation function and with one max pooling. Okay, now there is a chance that multiple convolution layers will be there, then my max pooling will be there. But a general architecture is that convolutional operation we have to perform. We have to apply this activation function that is called, up to this portion, it is called convolutional layer. We have to use convolutional operation, then we have to apply activation function. This summation of these two is known as convolutional layer. Then we will go for a max pooling or any pooling. So there will be multiple convolutional layer in one convolutional block. Okay, there is a chance that there will be 2, 3, 4 convolutional layers, then followed by one max pooling. Okay, or any pooling layer. So that is called convolutional block. So this is a convolutional block. Now, typically, that AlexNet and VGG16 type of network takes input image of size 224 cross 224. So we will treat at a number of nodes. So each pixel will be considered as a one node. So we are having an image of size 224 cross 224. So we are having that many nodes arranged in a tabular form, like this representation, or we will call it a matrix representation. Cross 3, it means it represents 3 channels: red, green, blue. If image is RGB, color image is there, so there will be red channel, green channel, blue channel. For each, there will be 224 cross 224 size of matrix. Okay, and each element in one matrix will represent a pixel information that will be treated as a node. Now, in convolutional operation, what we do, we try to use filters. Okay, because our task in CNN is to use filters. Okay, and to extract features. Our task is to extract features because we are doing feature engineering initially. So we will use filters. So filters are nothing but these are some kernels specialized to detect something, some patterns. Like if you want to detect edges, then there are edge filters. If you try to detect textural pattern, then there is a texture filter, Gaussian filter is there. Okay, so for example, if you try to detect edges, then we are having gradient based edge detector. There is a filter. Then we are having Sobel edge filter, Kenny edge filter, Pitwit edge filter. We are having so many edge filters are there. If you are using texture based, they are having textural filters are there. You are having Gaussian filter. You are having DWT filters. So we are having several filters. Okay, now these filters will be having some size. We call it kernel also. We will call it filters and kernel. Now, typical size of a kernel is 3 cross 3. Okay, a typical size is 3 cross 3. And the filter size will be decided like this. It will be like 3 cross 3 filter with a depth. It will be depth. Depth will be what? It will be number of channels decided by the initial layer. Its forward layer is this. The information is forwarding here. So okay, in this layer, it is having 3 channels. Then in this layer, we will be having 3 cross 3 filter with a 3 depth. Okay, so this is what a filter is. So it will be one single filter. So the size of this filter will be 3 cross 3 cross 3. Okay, it will be single filter because 3 cross 3 is a filter size with a 3 depth. And in a single convolutional block or in single convolutional operation, we can use multiple filters. We can use up to 64, 128, 256, 512 filters, different type of filters we can use. Okay, one filter is having this size. Okay, now what happens in this convolutional operation, it will select this 3x3 block, okay, from each channel, and it will be like a sliding window protocol. We will see initially it will start from here, it will go till here, from everything it will grow from first position to last position. It will choose a 3x3x3 size matrix, 3x3 from here, 3x3 here, from 3x3 here, RGB. Now it will do element wise multiplication. The weight values of filter will be here, these are weights, this filter values will be updated, okay, these weights will be updated during the back propagation, okay. This weights will be multiplied with this information, plus this weight will be multiplied this information, plus this weight will be applied this information, and the summation will be done. So it will be nothing but it is Wx. W is this weights, X is this input information, plus B is a bias. Okay, and that then activation function will be that the value that calculated will be passed to activation function. Now it will pass to ReLU. Now let us suppose if this value is negative, then this activation function will give output as a 0. If this value is a positive, then it whatever value it is, the activation function will pass the same value. That is the ReLU function. Okay, now for a single filter F1, it contains 3 kernel, K1, K2, K3. Okay, so total 27 weights will be there, 3x3x3. Okay, total 27 weights are there in one filter. Okay, with one bias. For each filter, there will be one bias. So total 28 trainable parameters are there in this case. Now let us assume that if it is having 64 filters, then the number of trainable parameters will be 3x3x3 plus 1, 28 cross 64. So this will be the number of trainable parameters for one convolutional block with a 64 filters. Then we will apply activation function, then we will go for max pooling. We will see it later. Okay, so up to this portion, it is clear how activation is working. Okay, now let's discuss the input layer first. Now let's say whatever size is there, input size is there, this number of input size will be reduced to our specified size. In most of the cases, we use 224 cross 224, but you can decide your own. If you are designing your own CNN architecture, it is up to you, whatever input size you want to use. Then that input will be mapped to input layer. It will be a matrix representation. Okay, it stores nothing but pixel information. Pixel wise information, the input layer will store. Okay, so that spatial arrangement and all the relationships should be captured. Okay, for a grayscale image, the input size will be height cross width cross 1, and for RGB image, it will be height cross width cross 3 channel. Okay, so this is the input layer. Now, let's take an example. It's a input channel. Look at here, it's 9 has been stored. It's a 9 image. Okay. Now let's say if it's a how the representation look. It's a binary image, so the value will be either 0 or 255. Why 255? In binary image, it will be 1. So the maximum intensity value can be 255. 8-bit representation is there. Okay, to represent a pixel in an image, we use 8-bit representation for one channel. For 3 channel, 24 bits are used, but it are separate. So for one channel, the number of values maximum possible is 0 to 255. 256 different values are possible. So 255 represents pure white pixel, where 0 represents pure black pixel. Look at here, this 9 has been like something like this. Look at here, these are white pixels, so it will be something like this. So this 9 will be represented like this. These are the input layers. Okay. Now, convolution. Now look at the convolutional layer. I have already said what is the convolutional layer. Purpose to extract meaningful information. We have to extract feature. We will apply convolutional operation with a kernel so that the features will be extracted. Working principle: one small filter slides over through the image to perform element-wise multiplication, and output will be gathered in a feature map via activation function. This is the mathematical representation where I into k represents the activation map, with x comma y represents the position of a pixel. It's a summation of mn. Okay, where it's a mn represents its I is the actual image and this k is a kernel. It's element wise multiplication with some sliding window protocol. I is the input image, k is a number of kernels and filters. Okay, and now O is the output. So convolution detects edges, line, texture, shape, patterns. We will see how it detects. Look at here. It's a virtual example. Okay, look at here. We have an input image of size to 64 cross 64, and 3 channels are there. So it is first red channel, green channel, blue channel. Okay, these are channel. Now let's say these. Look at assume this is a small sliding window is a kernel. That let's say to detect the edges, it is a kernel. Okay, so how it will done? It will slide through from first position to last position. At the same, it will slide through first to last position. At the same, it will slide through first and last position. All will be summed. This all should be summed at this summing position, and bias will be there. And based on the activation information, the feature map will be generated. Okay, look at here. This from 3 channel, it is generating 1 feature map. Now let us assume in this it was a single filter is there. Now let us assume in this convolutional layer we are using 64 filters. So here we will get 64 feature maps. Okay, for each kernel or each filter we will get 1 feature map, and the size of feature map will be decided by the size of image. If you are using padding, full padding, the size of feature map will be same. Okay, it will be decided. We will see how to calculate the size of a feature map. Okay, now look at here convolutional operation. It will be nothing but these are filters. Okay, 0.25 minus 0.22, 0.1, 0.017, 0.26 minus 0.03. These are filter weights. Okay, and whatever information we are getting, these are pixel values. So it will be totally calculated, and the sum value will be here. The sum value will be reflected here. Okay, this is the convolutional operation. Okay, now let's look at here. It's a visualization again. So this is the activation map. How it is activated? Based on that, it will for it's a center pixel. Whatever it is calculating, it is called receptive field. Receptive field means the area for which we are calculating for a particular pixel. So this center pixel we are taking, and for that we are considering a 3x3 window. Okay, so for center pixel we are considering it's a local neighborhood. Okay, and we are performing this convolutional operation so that this activation function will activate this particular neuron with some value. Whatever value here calculated, that will be passed to activation function. If it's a positive, then the same value will be reflected here. If it's a negative, then it will activate 0. It will write 0 here. Okay. Okay, let us assume if you are not doing any padding, then the size will be reduced by, because it has to calculate for center. So from up it is 1 less, from bottom it is 1 less, from side it is 1 less, from this side it is 1 less. So size will be reduced by, if it is 224 cross 224 and you are not using any padding, so it will be 220 cross 222 cross 222. The size will be this. Okay, so this is the convolutional operation. Okay, now what are the filters actually? So filters are the first. What are the filters? Filters are some small matrix representation used to detect specific patterns. So we are having age filters, we are having shape filters, we are having texture filters. Age filters will detect ages in an image, shape filter will detect shape, and texture filter will detect textural patterns in different direction. And the size of filter should be odd so that center can be, because we have to form the symmetry around a center. That's why the common size will be 3x3, 5x5, 7x7. These are 3 commonly used filter. Okay, now let's say for example this is a age detection filter. It will basically detect a horizontal age, a vertical age. Okay, because it's a gradient, na? This minus this, this minus this, this minus this, and sum of all total. It's a basically age detection. So feature map will detect different type of ages, shapes, and texture. Now let's take an example. Look at here. It's a input image of 6x6. We are using Sobel kernel. It's a Sobel age detection technique. It is Sobel age detection technique. Okay, it will detect ages. So what happens? We will select first these 3 window. This position we will select. Okay, then we will multiply 20 into 1 plus 24 into 0 plus 11 into minus 1. Look at here. Plus 19 into 2, 17 into 0, 20 into minus 2, plus 21 into 1, plus 0 into 40, minus 25 into 1, plus some bias information. The total value will be calculated. It is 3. Plus some bias information. Bias will be positive. So this total value is positive. The same value will be passed to the output map. So here we have written 3. Now for the second, look at here. The second, it will be sliced. Now how the window will slide? It will be decided by strides. We call it strides. Stride means number of jumping that we have to perform. The sliding window will start its processing with after how many pixels. If the stride is 1, immediately in the next pixel it will start. If stride is 0, then it will omit 24. It will start from this 20 from 11 to this, and center pixel will be 23. Okay. Now again it is same. Look at here. 1 into 24, 0 into 11, minus 12 into minus 1, 17 into 2, 20 into 0, 23 into minus 2, 40 into 1, 25 into 0, minus, and 13 into minus 1. The total sum value is 27. So 27 is positive value in ReLU activation function. If it is negative, then 0 will be there. If it is positive, then we will put positive information, the information that we got. This is called convolutional operation, and it will do from first position to last position. Okay, now the filter hyperparameters. There are 2 hyperparameters. First one is the dimension of a filter. So look at here. F cross F is a filter size, and C is a number of channel. Okay, if there is a 3 channel, then it will be F cross C. If in second filter, it will be same. In kth filter, it will be same. In one convolutional operation, you have to use the same size filter so that the generated map will be having same output. Look at here. Final, the filter size will be same. In one convolution layer, let's suppose if you are using K filters, K can be 64, 128, 256, 512. Okay. So if you are using, the filter size should be same. Okay, that is the main thing. Okay, and the one filter will be this. This is the called filter volume, F cross C. So total number of trainable parameters in one filter will be F cross C. If F is 5 and depth is, let's say, 100, then it will be 5 cross 5, 25 into 100, 2500 parameters will be there, plus one bias, 2500, 1. Now stride is the convolutional layer of pooling operation. The stride S denotes the number of pixels by which the window moves after each operation. So stride, look at here, it's the stride over, it is the first operation position. If stride is 2, so it has omitted one position, it has moved here. Then again, it will omit this, move there. That is called stride. Okay. Now these are the filters and feature maps. Look at here, the value. Now look at here. Okay, we are passing here now. So center pixel will be there. For this, the value will be calculated. Look at here, for 6 axis, it is generating 4 cross 4 output. Now if you want the padding, because if you want the same size output, then you need to do padding. So padding means we will pad 0 values in the outer side of this input slice. Okay, that is called padding to get a desired output shape. Okay, so that is called padding. So we are having 3 cases of padding, or you can decide your own. Valid padding, so P equals to 0, it means there will be no padding. If the same means it will be decided with the strides. If the padding size will be decided by the strides, it will be the size will be summation of I by hash. So it will be I by hash, and it will be the ceiling function of that. So output function is mathematically convenient. So basically, it's also called half padding. We will padding it half, and in full padding we will do for all the pixels. All the pixels should become the center pixel in convolutional operation. So the padding will start from 0 to f-1 and end at f-1. Okay, so maximum padding is there. Okay, so there are 3 cases of padding valid for 0 padding, half padding, and full padding. Okay, now look at an example. These are the how it is detected. Now this is the filter, this is image. We will pass this filter in image and we will get the output. Okay, now let's take an original image. It's called Lena image, and we have used this filter. It is called sharpen filter. It sharps the image. We have used this filter. Okay, in this image, the output is this. The image has been sharpened. Okay, now we have used Kenny edge detection here. Okay, so look at here. This is the Kenny edge detector. We have used edge detector in this. So look at here. The edge has been detected. Here the strong edge has detector is there. It is basically detecting horizontal lines. Okay, look at here. The strong edge has been detected. So what we have done, we have used these kernels and we have passed this to entire this image in sliding window protocol. So edge has been detected. Okay, now let's say this is kernel operation. Look at here. It will pass one by one, multiply with kernel, and feature map will be generated. This is called feature map. Okay, now edge detection using kernel. Look at here. It's a kernel we are changing, then edge detection is changing. There different kernel, different output. These are activation maps or feature maps. It is first feature map with this kernel. It is another feature map with this kernel. It is another feature map with this kernel. If we are changing number of kernels, if number of kernels are 64, then you will be having 64 features. Okay, look at here. This is the identity filter. It means whatever image is there, output will be same. These are edge detection. These are 3 types of edge detection. Look at here. It is detecting edges. Then we have sharpen filter. It is sharpening the image. Then we have box blur. Then we have Gaussian blur. So it is blurring the image. So to get the relationship. Okay. So these are the filters that we use in convolutional operation. Okay. Now strided convolutional operation. Look at here. The position is 1. Stride equals to 1. So it is changing in one position every time. Stride has been it has omitted here. So this is generating the feature map. This is the convolutional operation. Look at here. It is calculating. Since stride is 2, the size will be, look at here, how many it is. Stride is 2, so it will be I by S. Okay, so look at here. I is basically 1, 2, 3, 4, 5, 6. We have total 7 and minus 2, so total 3 by 3. It is upper 7 minus 2 because there is no padding. Okay, so it is 5 by 3. Filter size is there. Sorry, stride is there. 5 by 2, so it is 2.5, and our ceiling value will be 3, so it will be 3 cross 3 feature map. Okay. Now look at here. Look at here. Now what happens if the level wise in the first convolutional layer, it detects filter images like this, features like this. When we increase the number of layers, we will go more convolutional layers. So it detects the patterns now. Look at here, it is detecting the entire wheel area. Okay, this is how the layer works. So earlier layer extract textural or deep or earlier layer extract edges or shape features, and the mid layer higher convolutional layer detects the broad or abstract features. Okay, see, so now next we are another thing is that is called pulling. So what is a pulling? Basically, the pulling layer is downsampling operation, because number of filters, number of in activation map, in feature map, there will be high dimensional data now. Because if we are using 64 data, then 64 dimensional feature map will be there. 64 feature maps will be there. So number of trainable parameter will be very high. To downsample the number of trainable parameter and to fast the learning process, we go for a pulling. So there are two types of pulling, max pulling and average pulling, and there is one more global average pulling. So what max pulling? It will select a 2x2 matrix. It will be decided with a size. If you decided max pulling as a 2x2, so it will select 2x2 matrix in feature map. Okay, and out of 4, it will select the maximum value and put it to the output value. Okay, so that what happens? The size will be reduced by half in both ways. If you are using 2x2, then the width will be divided by 2, height will be divided by 2. That will be the output. If it is a 6x3, the output will be 3x3. Okay, if you have selected 3x3 max pulling, then output will be 2x2. Okay, so at the same time, it is considering the maximum value in local head, so it is preserving the detected feature, but at the same time, it is reducing the dimension in a drastic way. Average pulling, it will sum up all the values and divide by 4. The average value will be passed. Okay, so these are two pulling layers, max pulling and average pulling. Now, how we are applying this? Look at here, 2x2 max pulling or average pulling. Look at here with a stride 2. Stride 2 means we have to omit this position. One position, we have to left this position, we go to this side in both horizontal and vertical ways. So first it is this 0.1, 0, 0, 0.5. So the maximum value is 0.5. So 0.5 has been mapped. Now we have to leave this, stride is 2. So 1, second position we have to start. So it will become this 1, 0.4, 0.4, 1.6. So maximum value is 1.6 here. Now in downwards, it is with a stride 1. So it will start with the second position, 0.3, 2, 0.24. The value is, maximum value is, look at here, the maximum value should be 0.4. It will be 0.4. Okay. Now 1.7, 1.1, 1.1, it has been wrongly written. It will be 1.7. Okay. Now look at here. This is the calling function. If you are using TensorFlow, then you can decide the pull size. It is 2x2, 2. It is 2x2 with a stride 2. These two you can define. You are using 3x3. It will be max pulling. Okay, look at here. We have written max here. You will write average, then it will be average pull. So it will do 2x2 kernel with a stride 2. Okay, this is how we call it, kernel size. Now look at here, understanding the complexity of a model. If CNN layer is there, we are having pulling layer, we are having fully connected layer. Look at here, in convolutional layer, input size is I cross C. It's a in length, it's a image size. It should be a squared shape. So I cross I and C is a number of channel. And output will be O into O, and K is a number of filters that in this case we are having. K filters we are having, convolutional layers. Here in pulling layer, I, C, and it will be O cross O, C. There will be no trainable parameters in pulling layer. And in this case, number of trainable parameters will be decided with the filter, number of filter. It will be C cross F plus 1 into K. Okay, look at here. So these are the illustration or complexity of a CNN layer. How, and in case of fully connected layer, the number of trainable parameter will be number of input node plus 1. That 1 is bias into number of outputs. So it will be n in plus 1 into number of output. These many connections are there. So these are the trainable parameters. So this is how we calculate the number of parameters in each layer. Okay, it will be governed by the number of filters. If filter size is F and C channels are there, so it will be F cross C plus 1 bias into number of filters. Look at here. Now we have 3 ReLU functions. We have said now there is a ReLU, okay, which maps to 0. So there is a chance that there will be dying neurons. Okay, so what happens? We will go for a leaky ReLU. Leaky ReLU, what it does, rather than making it a 0, it will keep it alive by multiplying the Z value with a very smaller E value. It will a very smaller E value. E is a very smaller, it is near to 0, but not 0. It will multiply Z so that the negative Z value will be near to 0. Okay, but it is not 0. Still neuron will be active. In leaky, in exponential ReLU, it will map a exponential function here. It will be exponential. If the value is large, it will be constant here. If the value is smaller, it will try to map it to 0. Okay, so we are having three ReLU function: ReLU, leaky ReLU, and ALU. It is exponential ReLU function. Now we have another function that is called softmax. Softmax function basically decides the probability, or it calculates the probability from the last layer. Okay, so it will be the probability. The softmax function will give you the p value, okay, which will be the probability from class 1 to class n. Okay, basically it's a logistic function. It's a generalized logistic function that takes input vector and scores x into Rn. Rn is where n is the number of output, where p is the probability in Rn. N is the number of output classes. Okay, and pi will be decided like e power xi. Xi will be input from previous node, where summation of, look at here. First, I need to, so look at here. These are the, let's say these are the x1 to xi, and these are the output. Okay, so it will be calculated like this: e power xi over summation of j to 1 to n e power xj. Okay, so it will calculate the probability value of one node with respect to all. Okay, so we have already discussed ReLU function. The range is minus infinite, 0 to infinite. Okay, what it does, if the value is negative, it gives output as a 0. Otherwise, it gives the same value as output. Okay, but it comes with a dying ReLU problem, where if the continuous values are 0, then there is a chance that output neurons will be dying. They can die during training and never active again. That is the main problem. To avoid this, we are using leaky ReLU. So in leaky ReLU, we are using some multiplier there. Rather than using 0 value, we are using some multiplier e, that is 0.01, or it is very smaller value, so that the value will be from minus infinite to infinite. But if x is very high, then there is a chance that it will go for the minus infinite. Okay, but practically it will be a very smaller value. Then we have this parametric or ReLU, or we can call it ELU, exponential ReLU, where rather than here we have applied 0.01, we have fixed. Now we are using a parameter that has to be trained. Okay, it was in leaky ReLU, it was fixed. Now it's a parametric value. Okay, now in this case, it was an exponential value. Rather than multiplying it with any parameter or any constant value, we will use exponential information, e value. So it will be minus alpha to infinite, because due to exponential, the value will be constant after some time. Okay, and it works very best in all cases. Now we have softmax function. So basically, I have already discussed how softmax function works. Whatever your inputs are there, it will try to map the value into between 0 to 1. The values will be mapped into 0 to 1 probability information. Okay, it is used in multi-class classification. So let's say if you are having 3 classes, and the value will be, output will be in 3 classes. Okay, look at here how softmax function works. we are having this inputs. Look at here. Let's say rand panda is there. So all the information will be calculated like this: ex 8.4, the value of, let's say it's 8.4, then the value of all the others will be summed over here, and thus total probability will be this. Okay, now let's say if it is cola, then it will be probability of this and divided by the exponential probability, e power all the values. So this is the softmax function. So types of traditional neural network, we have fully connected neural network. So fully connected is nothing but it is a fully connected. All the neurons will be connected to all the neurons. Let's say if these are 8 classes, let's say these are 10 classes there. So all the neurons are connected to all the nodes. This is called fully connected layer. Okay, now look at here how the features looks like. In low level feature, it detects edges, dark spots, shapes, corners. In mid-level features, it try to learn eyes, nose, some patterns. And in high-level features, it means higher convolutional layers, it will try to learn abstract features. It will try to recognize faces, architecture, shape structure, complex relationship. This will detect it. Okay, so mid-level feature, it will detect nose, eyes, mouth. In mid-level, sorry, in low level, it will detect nose, eyes, mouth. In mid level, it will detect wheel, license plate, headlights. And in high level, it will detect doors, window, and steps. Okay, these are the features. Now, 6 convolutional layer example, look at here. We are having 6 convolutional layer with corresponding input. It's a convolutional layer 1. Look at here, car has an input. This is a convolutional layer with different filters. Okay, then we are having ReLU activation function. Then again convolutional layer, ReLU activation function, then pulling. So these are the, this is how the filters look like, the output looks like. It is learning first ages to, it will try to predict the probability. In fully collected layer, it will predict the probability. Okay, up to this point, it is clear. If you are having any doubt, you can ask me at any point. Now, this is a basic architecture of a CNN. Up to this portion, up to this fully connected portion, we call a feature extractor, and the rest part, that is a called fully connected layer 2 output prediction softmax function, we call it a classification part. So our target is to design feature extractor part followed by a classification part. So feature extractor part will be having convolutional operation with the activation function followed by some pulling layers. Okay, so that it will extract features. Why we call it feature extractor? Because up to this portion we are using convolutional operation, so it will use filters to extract patterns. So that's why we call it feature extraction part. Once the feature extraction map is there, we will go for a fully connected layer to flatten it. So flatten it means we will convert this matrix representation, n-dimensional matrix, n-channel matrix representation to a one-dimensional vector. That is called flattening. This is the flattening information, so that these can be further reduced down to the number of classes. Then this if you are having 4 classes, then in output there you will be having 4 nodes. Okay, so I have already explained it. It's another example. Look at here, next gen. It's a LeNet model. It's a first architecture. Okay, that basically it's a introduced Yan Lee. I think someone is there. Look at here, Yan Lee introduced this LeNet model in 1998. Okay, it is having convolutional operation, then subsampling is there, then there is a convolutional operation, subsampling, and fully connected layer is there. So this is the, basically it is having one convolutional layer, one subsampling layer. It means subsampling layer, it means it's a average pulling. Okay, it's a pulling layer, nothing more. So one pulling layer, one convolutional layer, another pulling layer, then one convolutional layer, and then fully connected layer. This network is known as LeNet. Okay, then we are having LXNet. It was one of the most popular net at that time. Okay, so LXNet. Okay, this net was very simple. Now it was basically used for digit recognition only. Okay, now it is LXNet. In LXNet, Alex has been Alex and his, I think 3 or 4 along with him, they have generated their network. It is having basically 7 layers, or I think 8 layers. So one convolutional layer is there, then it is a max pulling, then there is another convolutional layer. It is having 3 convolutional layer. Okay, then basically it's a convolutional layer 1, max pulling, convolutional layer 2, max pulling, then 3 convolutional layer, then FC layers, fully connected layers. So this is the architecture of LXNet. These are all architectures are publicly available. Okay, you can you don't need to implement it. You can directly, there is a function, you can call it. In Capstone project, I will demonstrate how to call this function and how to implement everything. Okay, now we are this VGG16. So in VGG16, it's a basically visual geometry group designed this network. It is basically pyramidal network. Look at here, it's a pyramid like architecture. Okay, then initially the VGG16 was designed to classify an image into 1,000 classes. Okay, so why VGG16 is called? Because it is having 16 trainable, it is having 16 layers. Okay, look at here, 2 here, then 3, sorry, 2 here, then 2, then 3, 2, 2, 4, 3, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total 16 layers in which trainable parameters are there. So that's why we call it a VGG16. Okay, this is the one of the most suitable layer model for image processing. But right now people are not using it because earlier it was performing very well. Now right now also it is performing very well, but there will be no novelty of if you are doing any research work and doing any task and you are using it for a research purpose. For your any normal purpose, you can go with this. VGG16 always performs well in case of your image related task. Okay, now there is a next gen that is called ResNet. In ResNet, they are used residual blocks. So what are residual blocks? In VG16, there is a problem called vanishing gradient, because error will be calculated here. That will, the gradient of error will be back propagated. Na? So the depth is very high. Okay. So what happens up to this portion? There is a chance that error will be 0. So there will be no mitigation in this layers. Bottom layers, there will be no mitigation and there will be no updation. The weights will be freezed. Okay. So the weights won't update, then these layers will not bring. That's why I call that is called vanishing gradient. To reduce that, it uses residual block for skip connection. So errors can backpropagate and vice versa. So it's a residual ResNet is designed in 2015. The main concept is to avoid vanishing gradient and degrading problem. Okay, so it uses skip connection. Skip connection means whatever input you are getting here, the same input will be passed to the another convolutional block. Okay, so that there will be while going backward, there will be no loss in the error propagation. Okay, design, it's a basically similar to GoogleNet. Then there is a ResNet architecture. So this is a ResNet architecture with a 15 trainable layers. Look at here, we are having, this is having one convolutional layer, then we are having 9, then we are having 12, they're having 18, 9 plus 1. So total there will be 15 layers in ResNet. Now there is a DenseNet architecture. In DenseNet architecture, it uses dense block. Dense block means fully connected blocks. So it uses convolutional block followed by dense block, convolutional block, then polling, then dense. So this is an architecture of a DenseNet. It is already available. You can use. Okay. Now look at the comparing the complexity in terms of a accuracy as well as a complexity. It's a number of, it's accuracy, and it is basically its number of trainable parameter with. Look at here in millions. The LXNet accuracy is less, number of trainable parameters is also less. Look at here in inception, accuracy as well as number of trainable parameter is very high. Okay, so this is a whenever we go inception 4, V4, inception V3, the depth is up to 300 layers. So number of trainable parameters is very high. So models are complex but performing well also. Now these are some real world example of a CNN. It can use in medical imaging. It can use in autonomous vehicle. It can use for facial recognition. Most of us, we can use it for a facial recognition. Okay. In our whatever we call it, a facial recognition in our mobile as well as in all the facial recognition devices we are using it. We can use go for a image classification task. Okay, object detection, semantic segmentation, video surveillance, agricultural monitoring, industrial automation. It can do all this CNN can do all the real world. It can solve all the real world problems related to these fields. Now, and the third section is recurrent neural network, RNN. Okay, so what is a RNN? Basically, RNN is a recurrent neural network. Now, when we are talking about CNN, there is a problem. CNN can't store the memory. CNN doesn't have memory. Okay, it can't store information. When we are simply extracting the pattern, now we are not learning anything. Pattern will be extracted and the weights will be updated in such a way that probability of a particular class will be adjusted. Okay, but when we are talking about patterns, now for example, if we have to work on a text information in which the order matters. Look at here. Order matters. Now, let's say if I have to predict a next word, I want to eat a mango. So I want to eat the mango. Okay, so the order matters now. So that's why there is a dependency. Whatever you want to predict, it is dependent on first 3 words. And CNN can't hold the dependency. It can't capture the dependency. So we use recurrent neural network. Okay. Now let's see what is a recurrent neural network. So we have already discussed what we have already discussed. Basically CNN, how it works. Okay. So for, let's say in image classification task, it is 1-to-1. We are having one image and we have to predict it to or map it to one class. Okay. So first fixed size image will be there and we have to predict the output class. It is called 1-to-1 mapping. Okay. Now what happens in 1-to-1 mapping? But that 1-to-1 mapping won't work in a textual or sequential data. Now sequential data, it means text. The cat sat on the mat. Now let's say we have to predict the mat. Now in this case, if we change, if CNN works randomly, it won't take the sequential information. The cat sat on the mat. These order matters. Okay. Now in a speech, audio sample over the times. So what we are speaking, it is dependent. What I am currently speaking, it is dependent on a previous information. So it is having long dependency. So CNN can't deal with the dependent values or dependent information. Same like stock price, how stock price is fluctuating, it will be dependent information. Like EEG signal, heartbeat signal, or EEG brain signals are there. So all this information, these are sequential data, and CNN cannot work on a sequential data because CNN work on unstructured raw data like images. Okay, why? Because this X5 is dependent on X1, X2, X3, X4, and it's a time-based information. In timestamp 1, the was there. In timestamp 2, cat was there. Timestamp 3, set was there. Timestamp 4, on was there. Timestamp 4, the was there, and we have to predict what will be in the timestamp 6. So that prediction, because in CNN there will be no memory, so it can't predict the sequential data. Okay, now let's suppose if we want our model to write down the caption of this image. The caption of this image will be several girls holding umbrella in the rain. It will be something like that. Na? Several people with umbrella walk down a sidewalk on a rainy day. It's a caption of this image. Now what happens? Look at here. How this works. CNN how works? It will take image. If you will try to predict, it will predict several. In another case, if you have trained like detecting people, so it will detect people. In some cases, it will predict width. In some cases, it will predict umbrella. But these are not related. We have to, if we want to generate a caption, this should be, this several will pass, this same information, this people information will be dependent on several. This width information is dependent with people. This umbrella information will dependent on this width. So all this information are interdependent. So we need some memory to hold this dependency. Here comes recurrent neural network. Okay, so with this model generates people, we need to way to tell the model that several has already been generated. We are detecting people, so we have to tell several has already generated. With we are predicting with, then we will tell the model that several people has already generated. Umbrella, then we will tell the model that several people with umbrella has been already generated. So the output will be several people with umbrella. Okay, so how it works? So we will create connection. Look at here. So whatever in output is there, it will pass here. We will pass it here. It will pass it here. It will pass it here. So it's a basically one hidden layer. It's a single hidden layer. Okay, or we will call it a hidden layer where the same information is looping. Look at here. X is there. Image is same. Input is same. Look at here. Input is same. But the input, what we are predicting, the same information we are passing through a loop. It is called recurrent neural network. Okay. So the information that we are predicted at timestamp t will be passed to the prediction for another timestamp. Okay, so this is called one-to-many. Now there are different neural networks, recurrent neural one-to-one, where it will be classification task. One-to-many, it will be image captioning task. Okay, input will be one, generate many information, caption. Many-to-one, it means, for example, we will give three input and we try to find a single output. That is called sentiment classification. Okay, or another word, sequence of word. Let's say in sequence of word we will given and we will try to predict the sentence, whether the person was sad, happy, or sorrow. We can predict. Many to many, it will like machine translation. We will give in Hindi and try to generate in English. So it will be same input, same output. Many to many is there. Another example, it is for frame level video classification. So there are some examples. These are all are recurrent neural network. It is more like classification. It is captioning generation. It is basically sentiment analysis. It is basically machine translation, and it is basically frame level video classification. Now this is the same thing. Now real world application we have already seen: speech recognition, machine translation, chatbot, text generation. It is based on RNN, stock prediction, EEG, medical signal analysis, music generation. In music generation, it means you will pass a phrase of a music and you will try to predict the next phrase of a music. Okay, that is called music generation. These are some real world examples of RNN. Now core RNN architecture, look at here how it works. So we have same input for all the hidden. There will be multiple hidden units at a different timestamp t. Okay, look at here. Okay, so basically it's a loop structure. So what it is this? So how hidden? These two are same. It's a hidden unit at timestamp t, at a timestamp t-1, and there is a delay. So delay means while computing ht, there will be delay. Some delay, it means it's a time delay. Okay, so fundamental feature of RNN is the network contains a feedback connection. It is called feedback connection. Okay, when we ht we have calculating, we need the information from ht-1, the hidden layer at t-1 is time. Okay, that information is needed. That is called feedback connection, so that this hidden layer will form a loop. It's a loop. Okay, so feedback connection allow information to persist. Why? Because this ht minus 1 is information is persisting. Okay, we are having previous information at computing ht. Okay, that's why. So this is the core architecture of a RNN. Now let's how ht is computed. So look at here, ht will be computed f of, it's a function of xt. Xt, you know now what is, it's an input, and input will be same for all cases, because if we are going for a image caption generation or one to many. Okay, for many to one, inputs will be changed. Okay, in case of machine translation, there will be multiple inputs. Okay, or in case of sequential data translation, there will be in case of sentiment analysis, there will be multiple inputs. But in case of translation machine, what we call it, image caption generation, input will be one. So it will be input. So at this time t. Okay, so look at here, ht will be calculated based on xt or h minus t1, where this is a function, some function is there. It's a basically nothing, but it's a convolutional function. Okay, xt is input vector, where ht is a old state. We will call it a state, hidden states. Okay, the concept of time or sequential processing come into picture, because in old state, it was time stamp t minus 1, and at current state, it's the current time. Okay, so activations are updated on time based, time stamp based at a time. At a single time, one state will be updated. Okay, now look at here. This is the basic architecture of RNN. So how it is happening? Look at here. This represents copy. This represents concatenate. So this ht minus 1 is there. So let's say if you are using, we have to predict one sentence, one word from a sentence. Let the cat sat on the mat. We have to predict the mat. So then the first step, xt will be the xt minus, it will be the xt, it will be cat, xt plus 1, it will be set, and we have to predict on the mat. Okay, so it will be like hidden state is there. This is a convolutional function. It is fc layer with activation function, fully connected layer with activation function. This xt information and in hidden state, it will be merged, concatenated, and it will be passed to this active fully connected layer with activation function. It will give you output. Okay, then the same information, the information that here, it's a copy now, same thing. Whatever he going here, it will pass to the next hidden state. Same, whatever generated here will be passed to the next hidden state. So this is called recurrent neural network, because why? The feedback system is there. Whatever generated here will be given as an input to the next state. Next stage is nothing but both the functionality of these two are same, with the same hidden weights, but input may change or may not, but it will try to use the feedback given from the previous timestamp. Okay, this is called unrolling of this RNN architecture. Rope unrolling. Look at here, it's a weight, it's a hidden weight. WH will be same because all the hidden state will be having same weights. WI, it may change. It's a WI, it means we are having input, the weight to this, weight matrix to this. Okay, look at here, HT is passing here with a WH. Then we are having this WT. We are having a fully connected layer with activation function. We are generating YT. The same information will be going here, and in this way, it is going in the forward direction. This is called recurrent neural network, in which the current information is dependent on the previous information, and it is basically capturing the dependency also, long-term dependency. Okay, but the weight matrix, look at here, this weight matrix will be same in all across timestamp. Okay, this is RNN unfolding. It looks like RNN. Look at here. For timestamp T1, it will be X1. Timestamp 2, there will be second input maybe. We will see it through an example. Now, let's say it's a hidden state 2, and I have already explained it, okay, how it works. Okay, look at here. Now, let's take an example. How this input X will be given. Okay, now let's say we have to write so how it will be given. Look at here. So how I have to give as an input as a dog. Okay, so DOGS. So dogs will be there. So the text input cannot be given as a directly, because we need weight matrix. Okay, so for that we go for a one-hot encoding. So one-hot encoding means whatever vocabulary is available in your training sample. Okay, that will create a matrix-like representation. First word for a D, another word for O, for G, for S. So look at here, for D it is using 100. So position of D is here, position of O is here, position of G is here, and position of S is here. So for this way, it will generate a vector-like representation. It is called one-hot encoding. Okay, that one-hot encoding will be, look at here, will be passed to this hidden layer. Okay, Now its activation function, it is same, it's a hidden node, it's WH into H minus 1 plus WX into XT. Look at here. WH here, WX here. Okay, then this whatever AT is, we are using the, for activation function, we are using 10H function. Okay, 10H is your activation function. And for prediction, we are using again softmasks. So look at here, it's a DOG. They will at timestamp T1, we will give D as an input, timestamp 2, we will give O as an input, timestamp 3, we will give G as an input, and we have our target is to predict S. So look at here from D H here. So it will pass the information so that it can predict O. The same information will be passed here so that D and O has been predicted already. So G will be predicted. So based on D or G has been predicted, so it will predict S. So it captures the long dependency. So already I have told how hidden state works. So hidden states is nothing but it's a fully connected layer with activation function. Activation function it uses as a 10H, where WH is your weight matrix from hidden to hidden connection. Okay, weight matrix is same across all. Okay, then HT minus 1. Says HT minus 1 is basically your previous hidden state, past memory. Okay, then WX is your weight matrix from current input to hidden connection. And this XT is your input signal, and plus B is a bias. This is your activation function for a recurrent, this hidden unit. Okay, then we have softmax function. It will be same. It will be all the connection. Okay, WY into HT plus BY. BY is your bias. Now look at here how the RNN works actually. It will initialize. So initially it will H0 will be set to 0 because there will be no initial state at the 0. Let's say if you are 0th system, then the first state is that, first hidden state is that. The previous to that, there will be no hidden state. So H0 will be set to 0. Then process X, we will process because we have to propagate, the cat set on the mat. We have to predict, So will be there. Then we have to compute hidden state 1. So it will be 10H. So 10H will be same, WX into X1 plus WH into H0 plus B. Okay, then for X2, this H1 has been computed, this will be passed here. Look at here, H2 will be WX is same, weight matrix is same. Then the second vector, this X1 is one hot encoded vector. For it is one hot encoded vector for cat. Okay, so this will be same, and it will be element wise multiplication. Okay, plus WH into H1. Okay, so H1 was generated here, and WH is the weight matrix. Weight matrix will be same across all the hidden layers or hidden nodes. Okay, this weight matrix will be updated. It is the trainable parameter plus bias. So H2 knows both the and cat information. Then this H2 will be passed here, set. Okay, so that it can predict the on or met. This is how this RNN works. So look at here. It's a visual example of RNN. Input sequence is 2, 3, 4, 5, and target output is running sum. Running sum means for first state, the running sum is 2. Second state, it will be 2 plus 3, 5. For third state, it will be 3 plus 5 plus 2, 10. And for fourth state, it will be 14. So we have to find the sum at each state. Okay, now let's say. So how RNN works. At timestamp T1, look at here, at T1, H0, here H0 will be passed. So H0 will be 0. Initially, there will be no hidden state. Prior to this, there will be no hidden state. So H0 will be 0. Okay, look at here. So H0 will be 0. The running sum is, right now, it is 2. So it will be 2. And the predicted value will be, how the function, look at here. The function is W1 into X plus WH into 0 plus bias. So look at here. It will be calculate 2. And this 2 will be passed because it is predicting 2. So that 2 will be passed as a H1. Now this H1 is 2 and this 3. Okay. The sum will be passed as output. It will predict 5, then 5 will be passed to next hidden state. Then 5 and 5, it will calculate and predict 10, and the 10 will be passed to next hidden state. Then 10, it will compute, 10 is H3, so it knows how 10 is come. The total previous sum was 10, and current is 4, so it will run, and it will compute 14, and this 14 will be your current output, and output of this H4 will be 14, and this will be your output. Okay, this is how recurrent neural network work. Another example, let's say we have to, this hello is there, so we have to predict O at last. So input will be, let's say it will be like, it is one hot encoding, HELL, we have to predict O. Then there will be weight matrix. Weight matrix will be same for across all input. Okay, just input matrix will be changed. Hidden layer will be have, these are the hidden layer calculation. Okay, calculated through 10h function. Now it will predict h, after it will predict e, then from e it will predict l, from l it will predict l, then from o it will predict l, it will predict o. So hello will be at last it started with h and it has predicted till o. Okay, simply this is like this. E has been passed to here as an input, e has l has been passed here to as an input, l has been passed here to as an input to predict o as output. Okay, this is another example. Now back propagation through time. So how it is thus, because it will be also back propagation error, there will be error in prediction. It will calculate the error so that weights, the weights are what, these are the weights, the hidden weights are there, hidden layer weights are there na? We are using the hidden matrix, this wh, this is weights, which will be updated. So that will be updated through a back propagation through time algorithm, in which the loss function, loss for all the state will be calculated and sum up at one position, and that loss will be will be the gradient of the slots will be back propagated. That is called back propagation through time. Okay, this is an example of loss. Here the loss will be here y predicted, it is y predicted, and y, the difference between this is loss 1, then y2 and y2 predicted and actual, loss 2, loss 3, the total loss will be this total loss will be then back propagated through BPTT core algorithm through a chain rule. The chain rule is what? It's a nothing but it's a derivative rule. The total loss is there, and we have to find the derivation of this rule through all the weights. Okay, this is a dependent weight. Okay, and that will be done via Jacobian derivative function. So okay, using a Jacobian matrix. So that is the major. This Jacobian is very complex. It creates problem in this case. Okay, we will see what problem it creates. So look at here how this works actually. At first, initialize the weight matrix wx, wi, wh. We have initialized na. Then what we will forward propagation to compute the prediction. Prediction will be computed. Then we will compute the loss at each state. Then the cumulative loss will be generated and it will be back propagated. Okay, and the weight will be updated accordingly. And this process will be repeated until there will be the minimal loss or optimized loss. Okay, this is the total, this is the stepwise calculation. We are calculating at first step, we are calculating L1, L2, L3. The loss will be this. Then we are finding the gradient with respect to this loss. Okay, via Jacob matrix. Okay. Then the chain through, this is the loss in third state will be dependent on loss in two state. Loss in second state will be dependent on first same state and follow first state, and loss in first state will be dependent in itself. So it's a chain rule, chain through dependency. Okay, there is a truncated loss. So truncated loss means calculating this entire loss 3 at a time. What we will do, if the network is very large, we will divide into parts. One part we will calculate loss, for another part we will calculate another loss, and we will sum up it. It is called truncated back propagation through time. Okay, now look at here that the main problem due to Jacob matrix, that this chaining rule is there. Due to this chaining rule, the main problem is that the vanishing gradient problem. Look at here at t state at, the gradient was 1. Okay, whatever the value was there that has to be propagated, it was 1. When it is 7, it goes 0.7. T6, it goes 0.49. Up to T1, it is 0.08. Now assume that if number of hidden state are more than 8. So there is a chance that in this state, the gradient will be near to 0. Okay, that is called vanishing gradient. There will be no gradient here, so there will be no updation in the weights. So gradient will be reaching to 0. That is called vanishing gradient. In some cases, the gradient will drastically increase. That is called exploding gradient. Gradient will tend to infinite. Okay, so in this case, early steps learn nothing. These early steps where there will be no learning. Okay, in this case, the weights will be updated widely. Okay, so there will be no learning. So these are two problems that occurs in the RNN. One is vanishing gradient, another one is exploding gradient. Okay, so we have already discussed it. Now vanishing gradient problem, I have already discussed. Gradient sinks towards 0. Exploding gradient goes towards infinite. Root causes 10h function with a chaining rule. In this case, due to large weights, there is a chance that exploding gradient will occur. Symptoms, network stop learning at early layers. In this case, NAN weights will be NAN. there will be no weights. It's not a number weights or loss diverge. Okay, primary fix, vanishing gradient problem fixed by LSTM, GRU. LSTM is long short-term memory. GRU is graded recurrent unit. Okay, this ReLU function we can use, residual connection we can use, or to remove the exploding gradient, we can go for a gradient clipping. These are the solution that we can do. So gradient clipping means, look at here, it was the original gradient, so gradient Z into some threshold value. Typically threshold will be between 1 to 5 divided by mod of gradient. So in this way, the gradient that was going exploding, it will be reduced. It is called gradient clipping. Gradient will be clipped down. It will be cut down. Okay. So look at here, gradient clipping, clip by value, clip by norm. Look at here, clip by value. If gradient is greater than some threshold value, then we will use sine function into gradient plus threshold. The new gradient will be this. It will be simple, but can distort gradient. Okay. Now it's a clip by norm. Look at here, if norm of gradient, normalization of norm of gradient is greater than max norm, some value, then it will be G into max norm divided by norm. These are two methods where we can cut down this problem, exploding gradient problem. So the major advantages and disadvantages in RNN are, RNN can process length input. Okay, it can compute for a step T and in theory, okay, and it can use the information for many steps backward. Okay, model size doesn't increase for a longer input. If input is longer, the model size won't increase. Same weights applied to every timestamp, so that there is a symmetry in how inputs are processed. The major disadvantage with RNN is recurrent computation is too slow, very slow it is, and in practice it is difficult to access information for the many steps. Okay, these are some RNN problem. So if we have a time, or we can stop here. I can go with some example also if we have a time. Am I audible? Okay, is my voice is clear? If we have I think it already 9:30. So I have some examples. Image captioning was there, how to generate this neural network. So if we have a time, we can discuss this. Can anyone respond? Shall we continue or we can stop here?
Sir, we can stop now today. It's 9:30. Then again tomorrow we can start.
We can start here from, because tomorrow we will discuss some basics of this. There was two problem, vanishing gradient and exploiting gradient. We will discuss these two problem. Then we will go with the basics of NLP, followed by the how model can be developed. For example, how data set can be prepared, how that model can be designed, and then how deployment can be done.
Right.
So I will share this PPT with everyone. If they have any doubt, they can reach me out.
All right, sir.
Okay. Thank you, everyone. We will meet tomorrow at the same time at 7.
Thank you, sir. Thank you so much, and thank you, everyone. Good night.
Good night. Good night. Thank you, sir.